Stand here and help. Good morning. Good morning, everybody. If you could take your seat, we'll get started in about 1 minute. Oh, the team's coming up. Okay, I'm going to go ahead and get started with announcements as people filter in. Just have a few things to get us started. Some of it's repeat from yesterday. If you are a foreign national and have not checked in with the guard this morning, please do so. You have to check in every morning. We do have a mother's room upstairs, up above where the breakout rooms are, so please check in with the front desk if you need that facility. Also, just a reminder that we can only have drinks in this room. They don't even let the director do that, but we talked them into it. More specifically, Jamie talked them into it. Please don't make us lose that accommodation. We did. Oh, go ahead, Jamie.
It is on. You're on. Okay, everybody raise your hand if you can hear me. There we go. Let's try again, Karen. They were not listening to you. They're going to listen now. Go ahead.
Okay, sorry, I forgot the raise your hand thing. It's bad because my mom's a school teacher, so. Okay, foreign nationals. If you haven't checked in with the guard this morning, please do so. We do have a mother's room upstairs if anybody needs that facility. It's up above the breakout rooms, but they'll let you know where exactly at the front desk. We can only have drinks in here. We did find a yogurt container in here, and Jamie is watching you, so.
Yogurt is not a drink.
She seems nice, but it's Southern nice.
It's kind of a liquid, but.
I said it's Southern nice.
I'll be polite.
She'll come get you. A reminder that we're using Slido for questions, and we have polls during the breaks. I'll kind of try to spur you to go to do those at the break times. But if you don't have it already opened on your phone or your computer or whatever, please do so. Also, we again have lunch, food trucks for lunchtime. Today is Greek on the Street in Geno's. Everybody's really excited. All the APL people are really excited. The QR codes are here, and today you can pre-order both of them and let them know what time you want to pick it up. So you can kind of be doing that throughout the morning during breaks and stuff. And lastly, we have feedback boards outside in the lobby. It's to the right of the reception area. There's 2 big blackboards. There's Post-it notes on the table next to it. We would really love to get feedback from you guys about how you think things are going. There's 2 questions posted, so you can go answer those. Okay, and I think I am ready to hand this off to Wes and Jamie. Take it on.
All right, good morning, everybody.
Good morning.
Good morning.
We don't have our clicker. Oh, we got to get our clicker. Oh, there we go.
So, LSIC. LSIC's been busy. We've been busy this year. We've done a lot of cool stuff. This is actually an example of some of the really good stuff that's been happening. You know, the community, you guys asked for stuff, and there was a big conversation about, hey, we really want to know how to engineer for the moon. We really want to know, like, how to actually worry about building hardware. So what did we do? We created Lunar Engineering 101. Yeah. And I think that's just a great example of how you wanted it. Now it's here.
Yeah, so if you're, trying to onboard, figure out how you can be a part of this, lunar technology development, we got a lot of terrestrial technologies that are figuring out how they can have their place on the moon. This can get you your footing and give you some direction for some of the most critical things to consider. Pretty easy to find on our LSIC site. You go to lsic.jhuapl.edu, and then it's right under Resources, Lunar Engineering 101. You can find it right away. Watch those videos. If you have questions, if you want to see more details, there's resources, there's citations. Milena put in probably 150 citations into the paper that's about it. So You can
Yeah,
find all
I
the
actually, I
background.
want to give Milena a round of applause for this
Yeah.
one. Oh, we're gonna give Milena. This was a lot of work. And it's gonna keep growing and we're gonna keep adding to it if needed. And that is a great, tool that we have.
No, yeah, and, so yesterday, we heard a lot, we heard a lot yesterday. I don't know if you realize it. Was reflecting last night. From Clayton, we heard about the public-private collaboration and how we're driving towards commercials involvement, all this stuff. It's been a theme of ours for a long time. From John, we heard about lunar permanence and Blue Origin's stable vision. I was really impressed with not just, we're gonna try it once, if it doesn't work, we're gonna move on, but they're gonna try it and they're gonna keep to it, which was really, really great to hear. We heard a lot of kid and launch stories.
Yes.
That was really fun. What I loved most about yesterday, though, was that we saw stuff in flight and actually on the moon. This was our first meeting where we're able to see videos of tech that we had considered, 5 years ago. Maybe we could try to fly this. Maybe we could try to develop this. Bam, it's on the moon. It's operating. It is throwing regolith all over the place. So that was amazing to me. And we heard from Nikki talking about Lyft and how we work together for infrastructure that works together, right? That's pretty important. And today we're going to hear from all of you in the breakouts and the feedback that you give through the panel, or through the posters and the Post-its that Karen was talking about in the breakouts that we're going to go and talk. That's the stuff that we feedback and allows NASA, Nikki, to be informed when they're making decisions about things like Lyft she was talking about. So we're making that happen.
Yeah.
And we don't want to just talk about it. We want to talk about the people who are actually doing this stuff.
Exactly. So we've talked about 5 years. We've talked about the growth. Jason hit on this yesterday. This is a lot. When this was started, there was not 3,500 people. That's a little bit insane. And every month when we see the new members that are being added, it is insane to see how much we've grown. And with that, we want to get the community a deeper involvement to really start working together. Midwest do not want to talk anymore because we want to make sure we leave the rest of the time for our team that's doing the hard work. So we're going to pass it along and let Anthony start.
We don't want to talk, but we probably will still sometimes. So, or maybe they don't want us to.
All right, well, thank you very much. All right, so welcome everyone. It's great to see a lot of familiar ISRU faces and some new folks as well. We in the ISRU capability area are excited for the rest of 2025. We have a lot of great ways for you to deepen your community involvement as well. Starting with the ISRU workshop, we hope that you can join us on July 16th for our workshop, which will focus on the testing, interfacing, and funding for ISRU systems. So we'll hear lessons from successful networks of test facilities and see how we can apply those lessons to integration and testing campaigns for ISRU. We'll explore various oxygen from regolith systems and their interfaces, and we'll also discuss tips for securing non-governmental funding to help further your ISRU R&D. And we are also working the oxygen from regolith, or O2FR, system study. And the goal here is to enhance community understanding of ISRU at the system level. We do that by investigating the interdependencies between ISRU functions, as well as looking at how interface parameters move from one subsystem to the other. And the goal there is to promote compatibility of ISRU at the system level. So we hope you can join us. That will be a virtual event, and the registration will open in the coming weeks. Also, water ice. So water ice continues to be a topic of interest in the capability area, specifically understanding the form, distribution, and abundance of water on the moon, and how those inputs can enable better design for systems that can utilize those resources. And last but certainly not least are our monthly meetings. These are held the third Wednesday of each month. And if you haven't noticed, today is the third Wednesday of the month. But I'm telling you, don't click that link. Do not join. It'll be a very lonely place on Zoom.
This is the ISRU meeting, right?
This is the ISRU meeting, right? So we want you here, but do not worry. Come June, we will resume our normal schedule. And if you haven't been, they're great meetings. We host guest speakers from government, industry, academia, nonprofit organizations who will speak to their ISRU specialty. We save time at the end for you to interact with our speaker for Q&A. These meetings are also a great avenue for networking. So it's a large community. You're bound to run into someone who is working on a similar challenge as yourself. And if you'd like to share some of your accomplishments or your research or technologies, please reach out to us. We'd be happy to hear your interest in that. Oh, I guess I do the next slide.
I think that's what you said is really important. Not sure everybody understands it. Like, if you reach out and you say, I have a really good topic and I think it fits in, we most of the time will make it work, because part of our goal is to get all the information out there and get companies heard. So he means that when he says it. Reach out to us if you have something you want to share.
Yeah, I really do. And you can scan that QR code. That's our facilitator email. So you can reach out to us about speaking, about any general questions or comments, or even for subject matter expertise. We really will be happy to hear from you. And for our breakout, the theme will be from lunar regolith to Martian soil. You can see this lovely Venn diagram above is binning different technologies as applied to oxygen from lunar regolith, polar water mining on the moon, and Martian ISRU, and a combination of all three. So we'll discuss synergies between these technologies that could be applied to Mars, as well as key differences that should be accounted for. And we will also get into scaling. So how should we scale ISRU for a sustained presence on the moon, as well as supporting travel to Mars? We look forward to seeing you there.
Thank you. Good morning, everybody.
Good morning, Jibu.
My name is Jibu Abraham. I have the privilege of co-facilitating the excavation and construction focus group, along with Sada Hasnain, who's online. When we think about excavation and construction, it's the ability to tame and manipulate soil and structures. But before I get into some of these items that we're doing in the excavation and construction focus group, I want to just give us a sense of scale and the why for the first item here called link. If you were to sum up the amount of soil or dirt or regolith we've manipulated robotically between the moon and Mars, it'd be on the order of 70 kilograms. So less than one Jibus, less than one me's, right?
Good scale.
Now, if you needed to just prep the site for an average size house, 2,500 square foot house, right, before you laid any concrete, about how many dump trucks worth of soil do you need to move? What do you guys think? 6, 10, 1? You need about 15. Now, my Colorado School of Mines people who are here probably correct me, but on the order of about 15 dump trucks. Now, let's scale that to the moon. If you needed to prep the site for a 50-meter landing pad, right, you would probably need to move 150 dump trucks worth of soil. So that would fill this Kosikov Center about halfway, right? So that's orders of magnitude difference in the resources you need to manipulate soil and structures from where we are right now. And we can't do it alone. We've realized to do this, we really need each other. So we are partnering for an activity called LINC, Lunar Infrastructure Collaboration, where we think through what are the interactions to get to that minimum viable system on the moon. Not just an excavator, but excavator coupled with surface power, coupled with autonomy, coupled with ISRU, to make an ecosystem that works for this community from the ground up. So that's where LINC comes in, where we'll have regular meetings to support that. So if you're interested in thinking through what systems and structures and what interactions need to work together, and in particular, what do we need to do first, right? Before we can get to 50 people and your grandkids living on the moon, what do we need to do now the next 5 to 10 years? Additionally, we have a lot of exciting things going on. We have a maintenance and repair workshop in September. I'll touch on this in the next slide. And we have super exciting monthly meetings, right? Where are my E&C people? Anybody here?
Can I count myself?
All right, yeah, we're super, super excited, you can tell. And we meet on the last Wednesday of the month. Can you go to the next slide? I have the next slide.
You can.
Now, one of the less glamorous parts of excavation and construction is thinking about repair and maintenance. But if you don't repair and maintain your structures, they'll fail in the short term. So come to our breakout where we'll think through the business case for maintenance and repair, think through trade-offs that shape our approach, to the lunar systems? What are the risks and drivers? What systems and structures do you need available for maintenance and repair? With that, I'll hand it over to Sean.
Alrighty. Good morning. My name is Sean Young. I'm one of the co-leads for the Service Power Capability area, along with Julie Peck and Jacob Garrett. I think both are out in the audience somewhere. If y'all would wave. You'll hear me say a number of times over this that we are very interested in what you have to say about how the capability area is being run, as well as your any problems or issues you are having. So please come and talk to one of the three of us if you have power questions or comments over the course of this conference. So just wanted to give a quick overview of things that we are doing right now. So one is this study we are calling VSAT plus what. We heard a lot yesterday about successful technology demos on the lunar surface, and also heard emphasize the need to transition novel technologies into institutional capabilities and infrastructure that we can rely on. And we think the best way to do that is to get technology onto the lunar surface and test it early on, and proving that we can generate large amounts of power on the surface of the moon, I think is a high priority thing to be doing. But the question is, if you have all that power, what do you want to do with it? And what other technologies can you demo alongside it? So that could be other power technologies, or a tech from ISRU, ENC, or autonomy or sensors to better understand the lunar environment. So this is a very, we're in the early stages of this, and we're kind of in fact-finding mode. So if you have ideas about this, please come and talk to one of the three of us, and we will make note of it. I'll also mention, Jibu had talked about Link. It's on the ENC slide, but it's really cross-capability area. So I encourage you, once the announcement for those meetings come out, if you're in the power community, we definitely want to hear your voices there too. Also up on the slide, so save the date for September 25th of this year. That will be when our power workshop is. The topic is still tentative. Vaguely, and we need a better title than what I'm about to say, but we are considering power applications across scales. So really wanting to understand what the demand is for for small amounts of power all the way up to the multi-kilowatt scales of power. Again, if you hate that, if you love it, please come and talk to us. We'll be talking about it over lunch, and we want to hear about it. And then lastly, every month, like every other capability area, we have a meeting. It's the fourth Thursday of the month. We are always interested in hearing about new topics, about new technologies, things that you think the community really needs to hear about. So again, if you have ideas and want to pitch a topic, or want to pitch yourself or your technology and get the word out there about the things that you are doing, please come and talk to us. Or if you scan the QR code, you can email us. It'll hit all three of our inboxes, and we can set up a time. So And then right after this, we will be going into our surface power breakout. Everyone should be familiar with the Moon to Mars architecture document. We've been primarily focused here on power systems for the lunar surface, but with the idea in mind that Mars is along the roadmap at some point, we're interested in understanding what crossover technologies exist between Moon and Mars, and what additional work you need to do to make the transition. So with that, I'll hand it over to Lindsay.
I want to say something real quick. I think you're seeing in these breakout rooms that we are incorporating Mars. What I first want to say is, we love the moon. We're not leaving the moon. No. But I want to say that it's one of those, we're talking about Mars as a future destination. So we really want to start thinking bigger of what changes, what tweaks, what things do we already have that exist would work in both. So keep that in mind when you're going through this, because we really want to start looking at both of them.
All right, good morning, everyone. My name is Lindsay Tullis. I'm the LSIC lead for cross-cutting capabilities, along with Dr. Melina Graziano there in the front row. As everybody else said, if you'd like to have a conversation, please come find us. We are very, very busy in cross-cutting capabilities. We're a little different than the other focus areas. Instead of focusing on one particular technology, we take a sort of everything but the kitchen sink approach, I think. We talk about all topics that have to do with all the technology development on the lunar surface. So you will hear us talk about domains like environmental protection, dust mitigation, mobility, autonomy, sustainability, logistics. Those are really big topics, and I think you'll find us involved with most of the things that my fellow focus area leads here have talked about on some level. I think, and I hope you all will forgive me for saying that conversation within the community is important everywhere, but it's particularly essential within the cross-cutting capabilities community. We deal with such complex topics that touch everything. So the first bullet on this slide is confluence, because we have a really great space there for you all to talk to each other, not just to us, not just to NASA. We've had some really great collaborations come out of those conversations. We have a who's who page, we have event pages, we have topic pages. We really encourage you to check that out and essentially talk amongst yourselves, please. In addition, of course, if you'd like to talk to us, we do have our networking lunches at spring and fall meeting. It's always nice to put personalities and faces to those names we see on the telecons, so we encourage you to come chat with us, and also, of course, with your fellow community members. And as my fellow leads said, please volunteer to present. I don't think as a lead I've ever said no to anybody who has said they have a topic they would like to talk about. So we're interested in what you're doing. We want to help you promote that and find those collaborators that you need. So please reach out to us. The QR code on the screen there will get you our facilitator email. And thankfully that reaches our whole team so that you don't have to rely on my inbox skills individually. So within the community right now, we're working on so many projects, but I wanted to call your attention to a couple of things in particular. One, we are starting a conversation on lunar data, particularly what kind of data the community needs, as well as helping improve access to that data. There's a lot that's out there already. There's a lot more coming. Everybody's been following the CLIPS landings. That data is coming soon, and we'd like you to be able to get a hold of it if you can. So we're going to be starting that conversation on our July 17th telecon, accessing lunar data. We're going to be talking a little bit about how to access what's out there already and also some plans for the future. In addition to the lunar data, we're also talking about LINC. We're one of the members that are doing that work, support and collaboration. Particularly, CC is involved with mobility infrastructure and environmental protections right now. We're going to be reaching out on some of those topics to members of our community in the near future, but as always, if you have something to contribute, we want to hear from you. Again, QR code on the screen will get you our email. And particularly, within mobility, we are talking about, or we're interested in finding more about mobility roadblocks. Mobility is one of those technologies that is advancing access for everybody else. And so it's so foundational that we really need to get those roadblocks out of the way now so that those capabilities are ready when we need them. So again, we're going to be reaching out to some stakeholders, but please email us if you have thoughts or questions about that. Unlike the other focus areas, we do not do quite a monthly cadence on our telecons, although it has sort of ended up that way this year. We have so much to talk about. So June 25th, we are doing a telecon with the excavation and construction group on habitation. We'll be talking about cross-cutting capabilities topics within habitation. And then, of course, again, July 17th, accessing lunar data. Cross-cutting capabilities is also a little bit unique in that we are the only focus area that has our community-led special topic meetings. These are 6 areas where our community members actually lead generally a monthly talk over Zoom where they can really get into the details of these different technologies in a way that we can't reach during our regular telecons. So really great conversations happen there. If you want the details on those, like I said, they meet roughly monthly. Time, Zoom links, the emails of the facilitators are all on Confluence. So again, we encourage you to look there. There's also quite a number of resources that these folks have put together in our 5 years in LSIC, including our vacuum testing document, which I strongly encourage you to check out. It's very thorough, a lot of collective wisdom in that work. So that's a great place to reach out. In addition, like Wes and Jamie mentioned, Lunar Engineering 101 was the sort of the brainchild of Dr. Milena Graziano in the cross-cutting capabilities group. I'm told that there was some issue with the video streaming early on, so if you were having trouble with that, I think we have solved that issue. We really encourage you to go back and watch those videos again. We know that's a great resource for the community. I mean, if you have feedback about that, we're happy to take that as well. All right, and last but not least, the cross-cutting capabilities breakout room after this session. If you have tuned into our telecons the last couple of months, we've been talking about sustainability and the many, many actors who are working in that realm right now. We'd like to get into the details a little bit today. We sort of tongue-in-cheek call this reduce, reuse, recycle. I'm a child of the 90s. It was kind of a thing back then. But we're going to be talking about the specific details of what materials you would anticipate reusing or recycling on the lunar surface and the technology that is necessary to make that happen. And kind of the larger discussion about your role in the cislunar circular economy as well. And with that, I think Wes and Jamie are taking back over.
Yeah, we can take over. We've got a bunch of questions coming in too. I think a lot of these, what I wanted to kind of like bookmark at the end of this panel too, this is a lot of the stuff that you guys are planning on doing next, right? So this is a bit of a preview of some of the things that you can get involved with over the next year. So if something piqued your interest, I see some questions coming in that are relevant to some of the things that the panel was talking about. Yeah, join our meetings and we can start getting you in full, meet us here, come to the breakouts. That's how we can drive the direction of this so that we make sure that we're meeting your community's needs and then also feeding that up to NASA. So this is a lot of what's doing next. There's a lot of questions coming in. We're not going to have a chance to get to all of them because we're going to have to get to those fun breakouts where you can communicate more directly face-to-face. But the questions that we don't answer, our job isn't done when this meeting ends, right? We go back and do our day job. And we carry that forward into those meetings that the focus groups have, into our internal planning, into all the stuff that we're feeding back to NASA. So yes, all of that, don't worry if we don't answer exactly your question. Please put it in. We'll be able to still carry it into our future. One thing I did also want to say, one of the themes that came out from all of the panelists is that this is community-led and community-informed, right? So all the way down to CC, Lindsay, you were talking about the special topic meetings, which are led by the community. This is an amazing thing, right? This is something you want to do. We give you a little bit of a platform to do it, and then you can tell us all those amazing things that are down deep in the weeds that you need to know if you're going to actually be flying stuff to the moon. So that's something that I wanted to foot stomp on that. Let's see. I don't know. Are there any other really interesting ones you want to be?
Well, there's one, and I'm gonna let you guys talk
You all
to it
don't
too.
get
I
to
think
see,
it's a conversation between us. It's the highest upvoted is how is LSIC coordinated with other lunar community organizations? I actually feel like that's all we do, right? I know that sounds like we do all these amazing things, but we take meetings and have conversations. We're having joint stuff with Logic, with guests that come.
Yeggsla,
Yeah,
yep.
there's so many things that we're doing. We've been talking
Open Lunar's
to
here, there's a whole bunch of them.
Ascend folks,
Yep.
like all these conversations happen all the time in the background because we want to make sure that at least on our high level, we're not being redundant of each other and we're helping each other and we're complementing each other. I don't know if you guys want to hit on anything specific to a meeting where you've worked with another organization, but I know we have. Just can't think of them off the top of my head right now.
Well, you all can say that.
ISRU's big on
Yeah.
SRR, and I know we have some folks from School of Mines here, so I mean that's a solid one from the community. If you haven't been, highly recommend going to Space Resources Roundtable in Golden, Colorado. It's one.
Yeah, and we're the excavation construction focus group. We're connected to organizations like LSIC that organizes the Earth and Space Conference, as well as soon to have lunar guidelines for construction. So amongst the many other organizations we team up with.
Yeah, and I mean, if there's ever an organization that's not adequately represented, just let us know. We have a really low bar for entry into participating. We want everybody. I shouldn't say it's a low bar because it's high quality content, but it's a low bar for what you need to do to be involved.
We have another one here that says, where do inputs from the LSIC community go?
Everywhere? Is that
The
fair?
answer is everywhere and everybody. We do, everything that we get at this meeting gets put into a report. We share those out. We make sure we get high-level takeaways. It incorporates what we do into the next year. It incorporates what we do into our focus area meetings. You're getting this feedback every month. You guys are doing studies and reports under the LSI umbrella. I don't know if you want to
And
talk
we
about
do
that.
yearly surveys as well.
Yep. So all that is being incorporated. I think Nikki talked about that a little bit yesterday, that it is not going to a black hole. A lot of the things that we have done and the changes that we have made have been specific to feedback. Actually, one big one was why cross-cutting capabilities exist now, right? It used to be, my baby, extreme environments, and extreme access and dust, and I'm forgetting somebody, they're gonna yell at me, interoperability.
Operability, yeah.
And simulants. And we put them all together because we realized those are a little different. Those touch all the things, and we needed to treat that differently. And we decided to do that because the community said, the way you're interfacing these, it's not really working. So we're changing on a daily basis, I think, from feedback we're getting.
Yeah, and I just want to add too that I say this at every one of our spring and fall meetings. We read every email, we read every survey answer, we read every poll. Those things are not going into a vacuum. We are incorporating them into our meetings, into our conversations, and hopefully you're seeing those results in what we're doing on a month-to-month basis.
True story.
And if we're not serving the community, please approach us directly and email us if we're not hitting the interests from our month-to-month meetings or workshops. We really want to hear that. So we want to serve this community.
We live to serve. I've been really impressed. Like the meetings we've had so far this year have just been like, I feel like after 5 years, maybe I should know most of this stuff, but I'm still continually surprised at the stuff that's coming in. So thank you for that. There's a question about like the organizational structure of NASA and how we map into that. And I think we've always been infrastructure driven and technology development for the moon. And that's going to be something that has to happen no matter what organizational structure gets applied. Eventually, right, we have to do these technologies, and it doesn't matter if they're mapped into a different, I think in terms of math, so like if it's a different basis, it's still the same, points that we have to be hitting. So I wouldn't worry too much about that insofar as how we're directly mapping into that. There's stuff that we have to do. We all know that we have to do it.
Yeah.
Got any
No,
more?
I'm reading.
Oh, it's too much reading.
There's so much good stuff in here. A lot of this stuff could, okay. Here we go. Could the panel, let me read this one. Could the panel discuss how the focus areas specifically work together? If we just attend cross-cutting capabilities working group meetings, is that equivalent to attending the other focus area meetings?
Oh, I want to take this one for sure, because cross-cutting capabilities, that's why we exist, is to work with the other focus areas for sure. First off, we're always in conversation with each other. It's not on the slides, but I've had a hand in all the workshops that are happening this year. We all discussed breakout room topics and how we could coordinate those both in the spring and the fall and with each other. I would absolutely encourage at least the cross-cutting capabilities community to please, please, please attend the other focus areas workshops, attend their telecons. They need your input, frankly, in the same way that you need to know how your technologies are being incorporated in other places. And so I would say no, actually, if you're at cross-cutting capabilities, you're not getting the full picture, and I would really encourage you to attend the other events.
And I'll add that it's often very helpful to the capability area whose meeting you are attending if you're not intimately familiar with that topic, because it helps us to identify gaps in our own thinking that we might be missing. So, for example, if a dust expert comes into a power meeting, we're showing a connector mating and de-mating a number of times, and it's like perfect every time, and there's no dust involved, and someone goes, wait, how is that even possible? like those types of things are very valuable whenever we talk across capability areas.
I will say, there's a lot of meetings too, so it is absolutely okay if you don't attend every one of these, and you can pick back in and always ask those questions and drive it forward. I'm going to ask one last question because I want to give everybody time to get in the breakouts and do those one-on-one things so we can dive deeper. So just as a question to the panel, maybe go through quick and say, what tech or topic really drives you to work together? And we'll start this time at Anthony and work on down.
So I think a lot of what the other panelists have already shared links well with what we want to get involved with. You see?
I like that.
Well played.
So for example, with the excavation and construction link effort, a lot of the tie-ins are obviously the excavation rover. We need to get regolith into the ISRU pipeline. But with this new project, we can think a little bit more deeply about the next kind of generation of infrastructure. So not just what are the rover's capabilities, but how can our partner focus area help us to understand or optimize the pathways, so grading and paving roads between the excavation site, resource processing, the waste disposal, as well as to the end user. So lots of tie-ins there. The other focus groups as well, I would just say for power, evaluating trades based on different CONOPS of ISRU reactors. So some may be continuous, some are batch. Are you going to operate in the night, or do you just need to survive the night? And what are the payload capacities to get power there? And for cross-cutting capabilities, from a systems level, I think we've seen a lot of autonomy that can be done for ISRU testing of a specific system, but it would be great to get a little bit more involved for how autonomy would work at a system level, kind of governing the entire assembly line of ISRU. So there's a lot of good opportunities, and those will continue to grow with the other capability areas.
When we think about excavation and construction, just going back to that image of the scale of activities to get from moving 70 kilograms to multi-metric tons of kilograms of regolith, or to assemble a structure, all of our activities are really power hungry. So working with the power team is essential to ensure that we map, the construction activities map with the available power, as well as autonomy is very key. It's a key enabling agent that will support excavation and construction, and then working hand in hand with the ISRU community in terms of not only providing resources to ISRU, but understanding what kind of stock metals, we're thinking long-term, could come out of that process that we can use as an input to ISRU construction.
Yeah, if we're talking tech that, so a key input for us is, as G mentioned, sort of the demand for power. So both ISRU and ENC activities are very power hungry, and they have different needs for how often and how often they need to operate, which really drives what we are designing to. So understanding that demand in the near term really helps us figure out what we need to design to. I would say long term, you mentioned feedstocks. Having those feedstocks available to build cables, and there are projects out there doing solar cells from regolith. Understanding at what cadence those can come out really allows us to map out the available power over time that we can expect. And with all of that comes actual laying out sites, laying out where power will be generated for things like FSP. It needs to be far away from most of your activities. And so you need autonomy to interface with those things. And for most cases, you won't have humans up there, so you need autonomy to actually assemble everything. So yeah, all of that comes into power.
Yeah, for cross-cutting capabilities, it's not a single technology. It's thinking about the systems level approach. You know, when you excavate, are you kicking up dust? And is it settling on your science equipment? When you're building a shelter, you know, what's your radiation protection? What's your thermal protection? You know, when you're connecting power cords, like Sean said, you know, do you have a mating, demating protocol that will stand up to the environment? So for us, it's very much looking at not a specific technology, but about what enables all of these other technologies to function and to build this cislunar economy in a way that is sustainable and can go long term.
All right. I think it is time for breakout. Oh, we have a slide.
Yeah, we are exactly on.
Look at that.
The money.
Perfection. Early in the morning. Ooh, I'm not the MC. Karen's going to tell you what breakout's like.
Okay, I have two important announcements. One Jamie doesn't probably know about. There is a maroon with black hood Lexus blocking a visitor lot with a gate. The license plate is 5GN4424. It will be towed imminently, so if that's your car, you might want to run and do that between now and the breakout. So we have a 10-minute transition to breakouts. This gives you time to refresh your coffee and then go straight to your breakout room. The breakout rooms are listed here, so if you want to hear more about what our great team has been talking about today, go to that breakout room, whichever one is your favorite. We will be back here at 11 for a panel, so we will see you then.
Seriously, go to a breakout room. I'm going to come find all y'all.
They're going to be great. All right, everybody, I think we're going to get started. Oh, it's here. Sorry. Very simple. Can everybody hear me? Do I have to do the Jamie thing? If you can hear me, raise your hand. Good job. Yay, everybody. Good job, everybody. We are back, and we have our second panel of the day, which is advancing readiness. And I'm going to just go ahead and let Dr. Harry Van Halle kick off for us. Thanks.
All right, thank you very much. You got the slides? Okay, there we go. Thank you very much. My name is Harry Van Halle. I am with NASA Space Technology Research Grants Program, which is at the STMD. And I'm very excited to moderate this panel where we have three great presenters talking about three exciting projects. So we're looking forward to it. Just a couple of words about the program from which this project are from. So Lunar Science Technology Research is at STRG, and the purpose is to have universities lead efforts that are short in duration, have fairly high impact, so quick, significant impact on lunar surface technology development. They are university-led projects, but they can have teaming with other universities, nonprofits, and industry. These are early-stage technologies, so starting TRL is fairly low, but we do ask everybody to consider post-infusion as an important aspect of their projects. And that's why we're presenting this project to you today, to let you know of them and see if there might be some collaborative opportunities as these projects head toward the end stretch. So they're at about 1.5 years into their couple of years of project duration. If you want more information, lastly, there's a QR code and as well as the URL. So we have three exciting projects today. One less Christine Hartzell at the University of Maryland dealing with dust mitigation, Cynthia Song at the University of Pennsylvania, which deals with robot collaborating on the lunar surface, and finally Christopher Dreyer at the University of Colorado School of Mines, which handles ISRU. And without further ado, I'll turn the podium over to Christine.
All right, thank you. Okay, great. So I'd like to start by acknowledging the pretty large group of people that have been working on this project. We have research scientists, postdocs, grad students, and undergrads all working on this project, along with our technical point of contact from Goddard, Tina Montegarcia. Okay, so the technology that we're trying to advance is basically developing a lint roller for the moon. All right, so we would like to be able to remove dust from spacesuits as well as hard surfaces like solar panels using a technology that is actuated just like a lint roller. But instead of your traditional adhesive, we're replacing that adhesive with a synthetic gecko skin membrane. This is a membrane that is fabricated out of silicone. You can see an SEM image there in the bottom right corner that shows these kind of ridges on the surface of the membrane. And these are 10 micron scale type ridges that increase the surface area of that membrane and thus allow it to stick to different surfaces and in our case pick up dust. So the gecko technology, or gecko skin technology, has been used for a variety of different robotics applications, but the downfall of its use in robotics is that it gets dusty and then it stops picking things up. So we are basically exploiting that tendency of the gecko skin to adhere to dust. Synthetic gecko skin can be purchased or you can make it in the lab, which is what we do. And this technology could be actuated by an astronaut using it just like a traditional lint roller or by a cleaning robot. Imagine a Roomba driving around a surface where its active surface was this gecko roller. It does not require any power to remove dust from a surface, but we do require power to make that gecko skin reusable. So rather than bringing multiple sheets of this membrane to the surface of the moon, instead we're also trying to develop a mechanism to clean the gecko skin. The con-ops here is that your astronaut would have the gecko roller when they're out on their EVA, clean off whatever surface or spacesuit needs to be cleaned, and then when they return to the habitat, they insert that gecko roller into a cleaning appliance, and it becomes reusable. We look at two different technologies to clean the gecko roller. One is by embedding an electrodynamic dust shield underneath the gecko skin, and the second is just by spinning it really fast and using those centrifugal forces to kick the dust off the surface. Okay, so the objectives of our Luster project were to identify basically the key performance parameters at laboratory conditions and then look at the performance in more environmentally relevant conditions like ultra-high vacuum and also low temperatures. We also want to investigate the efficacy of cleaning the gecko roller and determine if that is really an advantageous route to go down or if we should view these more as disposable technologies. And then we're also looking at a prototype sensor that would indicate when the roller itself is saturated with dust and needs to be cleaned or replaced. This is a schematic of the test stand that we use to test the efficacy of the roller in laboratory and thermal conditions. What we have here is a platform, which is where we sprinkle the dust. Then we have a roller where the gecko skin is adhered to. There's a stepper motor that controls the translational motion of the roller across the test stand. And then we're also able to apply different weights to the roller to control the downwards pressure on the roller, which is one of the characteristics that we're interested in exploring for this design. In order to control the amount of dust on the surface, we have basically a small slide that we slide across the surface and ensure a uniform distribution of dust across our surface. For the results that I'm showing here, we're looking at about a 3 dust diameter thick layer of dust on the surface that we then try to remove. Here is a video of our gecko roller in action. The roller is going to be moving from left to right across the screen. On the right side, you can see kind of this white appearance. That's the dust. We use Lunar Highland Simulant 1 from the Exolith Labs. And then you can see an encoder that measures the slip of the roller, because we'd like to actually be rolling rather than pushing the dust across the surface. And then we have these 2 sort of saddlebags that are holding weights controlling that downwards force on the roller. So we're going to see the roller move from left to right. And you can quite clearly see that there's this darker region. That's where the dust has been removed. And then on the top and bottom of the screen, there's this undisturbed dust that has not been impacted by the roller itself. So that's what the roller looks like in action. We have characterized how much dust is removed as a function of the downwards force. So this is in 1 revolution of the roller, we're seeing up to about ½ gram of dust removed off of the surface when we have this about 3-layer thick amount of dust on the surface. We also characterize the slip of the roller. We can see that at low downwards pressures, there's increased slip. This makes sense, and it's probably due to issues with ensuring that the roller and the sample plate are perfectly level. The image on the right is an SEM image of dust adhered to those little wedges on the gecko skin, and you can see that the dust is quite a bit larger than the wedges itself, so it's not really embedding between the wedges. In our future experiments, we're going to be looking at the LHS-1D, or the dust simulant, which has a smaller particle size distribution, and we'll see how these results change for those smaller particle sizes. Our next steps are to look at doing ultra-high vacuum testing. So we're talking about sub-nanotorr vacuum testing levels. And this is quite a challenge when we're thinking about dusty vacuum chambers, dust in a vacuum chamber at these very low temperatures, or very low pressures. So we, one of the ways that we're trying to avoid getting dust into our turbopump is by actually mounting the turbopump at the top of the vacuum chamber to try to have gravity work with us and prevent the dust from getting into the vacuum chamber. We're also planning on baking out the whole system, and all the pieces of this system have been ordered. Many of them are in the lab, and we're starting the assembly. Here's a look at the test stand that's going inside the vacuum chamber. In this test stand, rather than moving the gecko roller itself, we're moving the dust underneath the gecko roller. So the vertical shaft there controls the downward pressure and downward location of the roller. And then we have a sample plate that translates underneath the roller and also presents the roller to the loading door where we can refresh the sample between experiments. Now, one of the challenges of doing this ultra-high vacuum testing is that the silicone that we use to make gecko skin has not been tested according to NASA standards at these very low pressures. So that testing is ongoing now. There are other silicone elastomers that are NASA vacuum rated, but we haven't made gecko skin with them. So we have a couple of options here. We're not sure what we're going to end up with in terms of the material that we use for the gecko skin. We're also planning to do thermal testing. We're very interested to make sure that this gecko skin works at low temperatures. One concern is that these small wedges may become brittle at very low temperatures, which would then decrease their ability to conform to variations in surface roughness, which would, of course, decrease its efficacy. Now I'm going to start talking about the different methods of cleaning the gecko skin. So we've talked about how we're going to assess the efficacy of the gecko skin performance under normal conditions. Now, can we make it reusable? So the two methods that we're exploring to make it reusable are first, embedding an electrodynamic dust shield underneath the gecko skin, and then second, basically just spinning the gecko roller very fast. So I don't think I need to go into a whole lot of detail about EDS functionality here, but in short, we are using a three leads in a square spiral. That's the form factor of our EDS leads. This is just laboratory conditions where we have EDS, gecko skin, and then the dust itself. So we are loading the dust onto the gecko skin in the normal way that it would actually be actuated. And this is a video showing the dust being removed from the gecko skin using the EDS. So EDS, always very pleasurable to look at, very effective. So it works even when it's embedded underneath a gecko skin. Here's our design for our rotational cleaning test stand. Again, we're just spinning the roller very fast about its axis. And we have this test stand to ensure that our dust will be contained in the appliance. We can control the speed of the roller, and we're making sure that we're not going to be inhaling any of our simulants. So in terms of TRL status, the initial was initially when we wrote the proposal. Current is our current state now. So we have shown that the gecko roller is quite effective at picking up dust off of hard surfaces. We did some initial work looking at ortho swatches, but we haven't repeated that using simulant yet. The EDS cleaning appliance is also quite effective at removing dust from the gecko skin. The rotational cleaning appliance, we're still building up that test stand, but we have demonstrated it at a lower fidelity and also seems to be quite effective at removing dust from a surface. So in summary, the gecko roller is a dust removal technology that requires no power to remove dust from a surface and can remove about 0.5 grams of lunar regolith per revolution of this roller. And to give you an idea of size, it's just the same size as your typical lint roller. And the roller can be made reusable via cleaning in a specialized appliance, either via EDS or high-speed rotation. And we're planning to do ultra-high vacuum and thermal testing this calendar year. In terms of partnership opportunities, we'd be interested in doing additional testing with optical surfaces, spacesuit materials, also help making new gecko skins molds. These molds are actually quite difficult to make. And then, of course, testing in situ would be the ultimate goal. So thank you.
Thank you. And next we have Professor Sung, who I believe is online. Cynthia?
Yes, hello. Can you all hear me?
So we need to advance the slides.
All right. Thank you. I'm sorry I couldn't join you all in person. This conference coincided with another one of my, some bit of travel, so I'm not able to join you there, but I'm really excited to share the work that we've been doing in the Trust project, and in particular, a multi-robot collaboration for being able to navigate extreme environments. And so if you could go to the next slide. The premise behind this project is that lunar environments are sandy environments, which are very difficult to traverse. What you're seeing here is a video of a legged robot, which people would consider pretty agile and maneuverable, but on these sorts of sandy environments, there's a lot of slippage, a lot of sinkage, and over time, errors accumulate in the robot's ability to do pose estimation, the control goes unstable, and the robot tips over. This isn't just a controls problem, but also a mechanics problem in the sense that this kind of uneven slippage and sinkage is currently relatively unpredictable, but also there are situations where the ground might be so hazardous that the robot is going to get stuck. And so the idea behind our project is to be able to deal with these sorts of situations. So if you go to the next slide, this is an overview of our different areas of research. We want to investigate how heterogeneous teams of robots can jointly overcome environmental hazards such as sandy environments and slippage and sinkage traps. So our project consists of two major components. If you click next, our first component is that we want robots to be able to measure and then use those measurements for planning ground interactions as they move around. One of the folks on our team is a geophysicist. He's interested in measuring reaction forces from ground penetration. And so we've been looking at how we can take those measurements and then directly convert them into models. At the same time, if you click next, we're interested in how robots can do these sorts of measurements on the fly. So as robots are going about their normal, regular missions, they can take sensing measurements that allow them to build these models. If you click next, then the second part of the strategy is that we want to be able to take these models and use them for planning. And the project is built on this hardware platform that one of our team members has created, which is basically this extendable arm that we can use to connect robots to each other in order to be able to produce pushing and pulling forces and assist and allow robots to assist each other to be able to traverse hazards. So the final component, then if you click next, is the planning. And so taking advantage of the models that we're and measurements that we're taking in strategy one, along with the particular hardware platforms that we're developing, we want to be able to then figure out how we can plan motions for these multi-robot systems to be able to rescue robots when they are stuck and also potentially preemptively deal with those situations. So if you click next, I'm going to lead you through our major results in each of these different areas. The first is that we've been doing quite a bit of work in trying to characterize the behavior of LHS1 simulant, which you heard a bit about in the previous presentation. What we've been doing is looking at what the ground reaction forces might be when a robot comes into contact with the surface. And in particular, the ground basically has a stiffness that is dependent on the packing density of the ground. One thing that we found, which is very interesting, is that because LHS1 has a very large range of particulate sizes, actually the range of stiffnesses that you might find in a bed of LHS1 is much larger than what you would find like on the beach or in spherical beads, for example. And so we've been trying to compare the measurements that we can take in the lab on campus, where we filter out all of the fine particles, as well as in the survey testbed, which I'll show in a minute, and where they don't, to see what are the differences between the behavior of these sorts of grounds when you have these different particulate sizes. What you're seeing in this plot, though, is two examples of the force displacement curves for the ground, and you're seeing a pretty linear relationship between the normal force from the ground and the penetration. And this is something that we can measure on the fly as robots are moving around on the surface. So if you click next, one of the things that we've been doing then is trying to do those on-the-fly measurements. This video should be playing. Maybe if you click next, it'll play. Yes, okay. And so what we find is that when you have robotic systems that have motors with relatively low gear ratios, then actually the current signal in the robots is a measurement of force. And so as robots are navigating over these environments, naturally they get force measurements from their contact with the ground, and we can use those measurements to take on the fly, to build maps on the fly of these environments. So here you're seeing some examples of these real-time force measurements that a legged platform is taking, which we then took to the AIM survey testbed, which you can see on the next slide, to see whether or not these algorithms are useful in real-life environments. So we've been working with people at AIMS to try to do these tests. And if you go to the next slide, you'll see this setup where we have now this robot walking around on this testbed, where we've we've manually constructed this environment where there are pockets of packed ground. Those are the red regions you see in the picture in the middle, and loose ground, that's the blue regions you see. And as the robot is walking over this environment, it is taking force measurements at the toes. Using that information, we can now reconstruct a map from the robot's walking, which is the map that you see on the right. And you can see that in terms of stiffness patterns, we get something very similar in the measurements as what we originally constructed. This is really useful, we think, because if you go to the next slide, what we can do is convert these maps into predictions of risk. And so we have some models for being able to extract from the stiffness of the ground and also the mass and the joint motions of the robot, what their predicted velocity in the ground is, and whether or not they'll slip and therefore have zero velocity, or whether they'll have enough traction to be able to move forward. What you're seeing here is the map that we constructed from the survey test converted into these velocity maps, which now we can start to use to construct obstacles as risk and do planning on. So if you go to the next slide, then if we want to move into areas that are hazardous for these sorts of robots, and we predict that they aren't going to be able to move reliably at all, we want to be able to create larger truss structures so that they can be more stable. If you click next, the video should play. And we're building these ideas on a hardware platform called the Spiral Zipper Arm, which is this extensible arm that can carry loads up to several hundred newtons. We can use this arm then to connect multiple mobile robots to each other to be able to create these leverage forces. And so if you click next, what we're doing now is modeling these sorts of truss structures as spring networks that allow us then to predict the displacements of these systems as these arms extend, while taking into account the ground reaction forces that we've measured on the fly. So if you click next, then again, we did some of these tests at the Ames Survey testbed. If you click next, yes. And what you're seeing here is some of our preliminary experiments using the spiral zipper arm to drag first just a box around in the bed and measure the reaction forces from the ground to make sure that they match the models that we've created. What you're seeing on the right is the force that's being exerted from the arm as this box is transitioning from hard ground into soft ground. And what you'll see is that the reaction forces are actually larger in the soft ground. This is because, if you click next, there is buildup in the material as the robot is being dragged around. This bulldozing effect is something that we do need to take into account in our planning algorithms. So to show you then our final, our system so far, if you click next, this is our current multi-robot setup. We have a two robot, in quotes, system where we have this mobile robot connected by a spiral zipper arm to this box with legs, which we're using to simulate another robot. You're seeing that the wheeled robot is able to drive forward. We're also able to move, contract the spiral zipper arm. When that happens, then the way that the system displaces depends on the specific ground robot interactions. So what you're seeing in here is that actually the legs on the box are able to anchor that box into the ground and drag the wheeled platform backwards. What we've also seen is that over time, through repeated tests, that the wheeled platform starts to pack the ground. And at some point, you start to gain traction and allow the robot to move more effectively. But after a certain amount of time with too much packing, then actually this hard surface becomes much more difficult to traverse. And trying to navigate how what happens as robots repeatedly traverse these sorts of environments can also be taken into account in these ground models. So if you go to the next slide, over the course of this project, we've had various conversations through LSIC and through LPSC to try to understand what the specific use cases are for the system. I think that what we know so far is that by connecting multiple robots together, we can start to use these interactions to be able to get more effective robot locomotion. And what we're looking forward to is in the next, by the end of year 2, we want to show active coordination between 2 or 3 robots that are connected by these trusses. If you click next, long term, and the reason I would be really excited to engage with people at LSIC is we think that there are implications both for multi-robot navigation, where now we can start to access more interesting environments that single robots may not be able to access. But also, because the robots are basically manipulating the ground as they're traveling, we can start to think about how these planners can also engage with passive loads, not robots, as a way to potentially deal with construction sorts of tasks. And so if you go to the last slide, then before I close, I just want to show the team that's been working on this project. This is a team from Penn and USC that's also been supported by a huge number of students who are very interested in this technology. And so we would also like to thank the Luster program for giving us the opportunity to work on it.
All right, thank you, Cynthia. Just a reminder, since we're one presentation away from our Q&A session, if you have any questions, please add them to Slido, and you can also upvote questions there. So we'll start after Professor Dreyer.
Okay, thanks everyone. I'm Chris Dreyer from the Colorado School of Mines. So I'm presenting here on magma. I inherited this as the PI. I was on the team from the beginning, but I inherited when Dr. Kevin Cannon had written this proposal and left Mines about a year ago and left the team. So it's a group of Mines professors from space resources like myself, from metallurgy, ceramics, and additive manufacturing, and we're teamed with Lunar Resources to advance an MRE, a molten regolith electrolysis concept. Our NASA collaborators are there from Glenn and Marshall. So what is MRE? This might be something known to everyone here, but it is electrolysis of the molten regolith directly at a high temperature, 1600 Celsius. In what we are working on, we are doing this directly in a vessel. Sometimes there's another form of MRE that's mentioned called cold wall MRE, where the intent is the regolith is, you're really doing electrolysis of a regolith melt pool. In this, the melt is directly interacting with the reactor wall. And so the material compatibility becomes quite important. Our objectives are to produce castable aluminum wire that then can be evaluated for its use as an additive manufacturing material. We're developing taps as a transfer mechanism between reactors and removing the melt from the reactor, the molten metal, and then also a quench wheel to produce the wire. We're doing a variety of things of evaluating the wire and evaluating materials compatibility. The approach here is a lot of this material compatibility, as well as the MRE itself is being done by the team from Lunar Resources. I don't think we have anyone here from Lunar Resources today, but from the Mines team, we have Ben Schneiderman, who's a postdoc sitting there in the middle. We'll also be showing some of our products here from the work in the show and tell. Ben's work in particular is this area of a thermophysical model using a code called FactSage. One of the concepts here is this is purely thermodynamics, but we produce a kind of reaction variable, the lambda oxygen, which is the fraction of oxygen extracted from the melt. And in this system, we're working with a Highlands simulant. We begin by extracting iron and silicon. Then we reach a point we call the transfer point, where we would extract the iron silicon, and then electrolysis continues, but this is primarily on aluminum. With the aluminum then being a lighter metal, it floats on top of the melt. As iron silicon's heavier, it sits beneath the melt. And then we extract that off. And this study on the thermal physics has guided us on the likely composition of the produced aluminum, as well as the iron silicon mixture, and other factors to be considered. So this slide here is has a lot on it, and I would encourage you to look at a paper we recently had published in Acta Astronautica that Ben led, but shows the composition trajectory as we move through lambda oxygen, just incrementally removing oxygen and seeing how the system reorganizes. And on the right side, the liquidus, the kind of as how the liquidus temperature evolves through the reaction, and the viscosity changes, all of which is very important for understanding the process of MRE. On the table on the lower left, a couple important things here are at the point where we find it optimal from analysis to transfer or remove the iron silicon. It is, you see the composition there. There is some aluminum in that. That is that aluminum begins to electrolyze while there's still iron and silicon present. And then in the final aluminum product, it is more than 99% pure aluminum, but with small amounts of silicon and calcium particularly. And that's actually okay. We'll find that the common alloys of aluminum do have iron and silicon and calcium in them, and you do want a bit of that to improve its workability, although you don't want too much. We've also done, I mentioned already, we've done viscosity calculations from FactSage. We've also looked at that in a couple other ways. We've directly measured the melt and molten regolith viscosity at mines. We have another paper coming out that's going to focus on this with different melts and different reduced oxides. Okay, moving on to material compatibility. This is another area we spent some time working on finding materials that are compatible with the melts and the metals of a hot-walled reactor. There's a number of different things we've looked at. So bottom line is alumina is a good non-reactive material, but we've also found that boron nitride is a pretty significant material that is relatively unreactive. We've also measured wetting angle, viscosity, and resistivity directly of various slags, molten regolith as well. This is a little bit of detail on this. This is melt in interaction measurements, where there's a small bit of regolith simulant melted in a crucible. We then look at the interaction of the crucible wall with the melt, and there's EDS measurements on the right that show the formation of iron within the melt at the wall, penetration of the melt into the wall, and the recrystallization. There's a lot that can be learned from this. In fact, there's another publication coming out that'll detail this. There's a little bit more closely on molten CSM LHT1 with hexagonal boron nitride. There is some reaction. We find this interesting thing that iron spheres develop at the wall. We are doing this in a slightly reducing atmosphere, a little bit of hydrogen in there to extract the oxygen that's being formed. But this has led us to conclude boron nitride is it is reactive, but it's a relatively good balance between non-reactivity and compatibility with a lot of the materials. This is a wetting angle measurement, and I think the two videos that are running on the upper left and right are interesting. On alumina, the molten regolith wets very easily. That cube flattened out. We have a little pressed cube of CSM LHT1 in the upper left. It flattens out and wets the entire surface of alumina. On the right, on boron nitride, it sits as a sphere like you would with a high surface tension material. Some other things going on here from our colleagues at Lunar Resources, where they are building the MRE reactors that we'll be working with there. They have built several different reactors, and they'll be working with various lunar simulants. We'll be working with them of integrating a tap into one of these reactors. We've worked with them to help select the refractory materials that are more compatible with this setup, and this is also an area of work of some testing that should occur, that we plan to have occur in October, or by October. So there are actually two distinct reactors, a extractor reactor, which focuses on the iron and silicon process, and then an aluminum reactor that focuses on producing the aluminum that is going to be integrated with a tap to produce wire. Going on to the tap, this is an area mines is involved in, and this is where a lot of material decisions come into play. We ultimately want taps that can be usable in a variety of situations, from extracting the iron silicon mixture, extracting aluminum, and also a transfer tap that just works directly with slag, partially processed slag, all of which must be compatible to withstand high temperatures, chemical compatibility of this variety of materials, and proper wetting behavior to ensure we have good transfer through the tap. We had initially thought we were going to use alumina. It is the best material compatibility, but actually has a poor thermal shock behavior, and we've done some testing that just when molten aluminum flowed through it, it just shattered instantly. I can show you some of the results of that in our show and tell. So we're moving to graphite, which has poor material compatibility or chemical compatibility, but good shock characteristics, and plan to coat it with boron nitride to protect it and have better compatibility. There may also be some boron nitride parts we'll work with. This is our tap design. There is a plunger there that moves through this the kind of Y joint, or you see from the reactor to the transfer point down to the quench apparatus. All of this is designed to be attached to the Lunar Resources reactor. So the entire system is quite hot. We've done various testing and prototypes and are in the process of testing this with aluminum. The focus here with this tap is on aluminum. There's various foundry tests that we have a nice foundry at Mines where we can melt aluminum, melt a regolith, and pour it through different tap designs. Some of this is just some videos here of that work in the foundry. And getting close to the end, the aluminum wire is actually produced here by a quench wheel. This is one design of a typical quench wheel. Lunar Resources producing that, so where the Mines tap delivers molten aluminum to this. The temperature of the molten aluminum must be dropped from the reactor temperature down to just above its melting point, and then the wire will be pulled off. At Mines, we are looking at some synthetic wire with compositions produced by the FactSage analysis. And we're seeing some progress here. We quantify this via the point we call the transfer point, where we decide to begin to switch to aluminum extraction, and that affects the residual amount of calcium and iron and silicon in the aluminum. And too much calcium, and it's too brittle to pull this wire the right amount, and it's actually beneficial. So we have at least one. We're expanding the scope of what we're looking at. And that's it, although since this was a panel, which hopefully we'll have some discussion on, challenges in advancing readiness. As a Luster project, what we're looking to do is produce technology development that then can be integrated into actual and lunar missions. I thought I'd put a slide here to talk about that. Of course, we're navigating through multiple different types of NASA programs. Many of them are structured around TRL level, from kind of really 3 levels: low, the middle, the mid levels, and then the high. And then we're also often navigating private funding. Like I have a partner who's privately funded, which brings with it some IP and competition concerns. I want to say some other thoughts on certain issues of readiness is that TRL is a factor. So most of the programs at NASA are structured around TRL. TRL presents technology development as if it's linear, but there's some ways of thinking about it as cyclic. I would say even a relatively high TRL system, especially if it never flown before, likely has open questions that really are more of a fundamental science question that still might need to be answered, even if the technology works. And then also there's timing issues. And then moving from one program to the next, there's always, does the next program available to you actually sync up with where you're at? Or is there a gap? I would say there's frequently a gap. At least you have a gap in time waiting for the next proposal to be selected. Sometimes it's advantageous to go to an SBIR, STTR after, say, other STMD programs. But in many cases, you're technically resetting, you're spending a year or more waiting for that to kind of catch up to where you were when you ended your previous program. So those are just some thoughts on that. And that's it from me. And I want to go to
Thank you
the
very
next
much.
phase.
Let's give a round of applause for all our presenters. And thank you for the program comments. We'll definitely take those into account planning for the future. We do have a few questions online. I'll pick the ones that are most applicable to everybody here with the time we have for questions. The most popular one is was there any special facility that you would have liked to have access during your luster program? If so, what was the barrier to access? And I guess also, if you did create a facility or testing device of your own, would you have preferred to have one that was sort of public use and you could have printed time on, for example, rather than do your own? So sort of two aspects, the same thing, about the facilities that you use and any that you would have liked to use but did not have access to.
So I guess in hindsight, it would have been nice to have used a thermal vac chamber rather than trying to get our own functional. I think that we probably could have gone down that route at the beginning of the proposal, but I think we just didn't know what was available at Goddard and how much overhead there would have been to try to get time on that facility and like use that facility. I'm not sure that this is so much a problem of NASA's responsibility as maybe just our responsibility to have explored other options before we wrote the proposal.
Yeah, I guess I've often encountered that there is something out there that would be good to have access to, but knowing how to get access to a facility, how much time it's going to take to actually get there and be able to use it is a bit too high, and it'd be advantageous if there kind of all the mechanisms to get access to something and then were low and easy to work with. I think in a program like Luster, 2 years might sound like a decent amount of a lot of time, but it's really not. And so 6-month delay, well, I don't know, any kind of delay just leads to your, as you know, Harry, kind of Luster's frequently requesting a no-cost extension. So.
I'll also add, I think our research collaborator has been really helpful in trying to facilitate our ability to use NASA facilities. So the survey test bed that we used for our tests, access to that was facilitated through our research collaborator. I think one of the facilities we might have liked to be able to use is there's also a slopes lab where we can also control the geometry of the terrain to be able to create more interesting environments than what we can do at Survey. And really, for us, the reasoning behind figuring out how we were going to test was kind of what Chris was referring to, just ease of setting everything up. Although I think once we have the system in place, we would still be really interested in trying to make those connections and testing on more interesting environments.
Right, thank you. The second question I'll ask is actually directed to Gecko Skin, but I think it applies to everybody. So what lunar environments were reproduced during your testing? And for those not included, do you expect to see any impact on performance and or lifetime, specifically for Gecko Roller, but all of them?
Yeah, so we are doing the ultra-high vacuum testing, and then we're doing thermal testing down to about -60 C. We haven't done either of those testings yet, but we're planning to do that this year. In terms of what environments have we not included in our testing, is we haven't included any plasma effects or like charging of the dust due to interactions with plasma or due to some controlled tribocharging that might occur. So those are environments that we haven't explored. I would imagine that the charging of the dust may make the EDS more effective. It may also make the dust stick to the Gecko roller a little bit stronger. Kind of unknown.
Cynthia, want to go next?
Sure. So the sorts of environments we've tested on are basically so far flat maps of LHS1 with ranges and stiffness with the largest range of stiffness that we can achieve with our machines on campus, and then manually with shovels and tampers at Servi. We have not looked at the effects of low gravity, which I think would have an impact on some of our results. And then the other thing that we had originally proposed, but we haven't looked at a lot yet, is what happens when there are also ice particles in the mix.
For us, the aluminum reactor and quench wheel will be, with the tap, will be tested in a vacuum chamber. That'll be at, it's in the -5 tour. So the interior of a reactor, of an MRE reactor, is at pressure, at an elevated pressure, so you have to keep that contained. It is, in fact, actually the process seems to be sensitive to the temperature, or sorry, to the pressure you operate at. So you wouldn't have an MRE reactor. You may not want to have an MRE reactor open to the lunar environment. You'll be evaporating a bunch of metals that you might prefer to have captured. There is an open question about whether, as you do the quench wheel with with aluminum in the lunar environment directly, that the aluminum and maybe some of its components will be evaporating away, and that's really a matter of how quickly you can quench the material. So, but we're testing that inside of a vacuum chamber in a lunar resources lab, and that's how we deal with the lunar environment.
All right, thank you. I think we're out of time, so thanks again for the panel. If you have questions to the individual researchers, please feel free to contact them. You know who their names and universities, you can just search them and find contact information, so please contact the researchers directly. All right, let's give them one more round of applause.
Thank you very much. And as you can see from your agenda, we're transitioning to a new panel. And so while we do that quick turnover for a minute or two, it is time for trivia. So go ahead. If you know the answer, raise your hand and I'll call on you. You have about 30 seconds per question. Okay, we got the first answer. Do we have everybody? Okay, you have to get this one, guys. Okay, is this the third or fourth question? I lost track. Is anybody a Latin expert? Please. One more? Or one more? Oh, you were busy too.
What does Maria mean in Latin? Shadows, women.
Okay, I think we're probably ready to transition to the next panel, so you can turn down the lights. Oh, we're doing one more question. Hold on. I think there's 4.
Do you know that guy over there?
Okay, everybody should know this one too. I think it's still on the table. Right there, yeah. And then the questions will.
Yep, we're good. Appreciate it.
All right, we are ready to transition to our next panel. This is the Getting Gear on the Surface panel, and I will turn it over to Adam Schlesinger.
Yep, thank you very much. Yeah, really happy to be here today. I'm the CLIPS, which is Commercial Lunar Payload Services Manager at NASA, and we have a great team of panelists that I'll introduce here in a bit. For anyone that's not familiar with CLIPS, NASA is partnering with commercial providers to deliver enabling science and technology to various locations on the lunar surface. And as part of that effort, we're hoping to, one, build the foundations of a sustainable lunar economy, but also, with that science and technology, help enable future lunar exploration and be extensible to other destinations as well. So it's a newer type of model that NASA is exploring, and it's also important to remember that we're really in the early innings still for CLIPS. We've had 4 delivery launches to date, and we have 8 active task orders for future deliveries and others in the queue and looking to be awarded. So again, just remember that we're in the early innings. So today we have 5 panelists representing 4 of which are direct CLIPS providers, and another is in support of CLIPS provider, all for missions that are to be executed in the future. But we will talk about some of the missions and deliveries that have already occurred. So let me just go down the line real quick and introduce everybody, then we'll get started with the specific presentations. So to my left, we have Joseph Marlin, who's the Chief Engineer of the Blue Ghost Lunar Program at Firefly Aerospace. Next to him, we have Niharika Agrawal, who's a Project Manager at Intuitive Machines. Then we have Steve Clark, who's the Vice President of Space Programs at Astrobotic. And we have Jeremy Fix, who's the Chief Engineer at iSpace US. And then Jackie Cortez, who's the Senior Director of Civil Space at Blue Origin. So we'll start with Joseph talking the Blue Ghost Mission 1 from Firefly Aerospace.
All right, thanks Adam, and thanks everyone for being here. I'm Joseph Marlin. I'm one of the 2 chief engineers on the Blue Ghost Lunar Program. Blue Ghost has had a busy year, and so has Firefly, and so we're going to go over kind of a retrospective of how our first mission went, and then a brief look ahead to what's next in store. Quick overview of Firefly first, fully integrated, vertically integrated company that also spans the launch, land, and orbit regimes of space exploration, with our Alpha small launch vehicle and our medium launch vehicle being developed in cooperation with Northrop Grumman to replace the Antares. Then we have the Blue Ghost lunar lander, which is what we're here to talk about, and then we also have our on-orbit line of vehicles, the Elytra vehicles. Some of the things that we like to talk about for Firefly that kind of point to some of the strengths that we have as a company is this vertically integrated model where some of the components that we fly on Blue Ghost also fly on our rocket, also fly on our Elytra space vehicles. We have a lot of in-house carbon composite structure expertise, from the very large structures like that MLV tank that you see in the picture to some of the smallest structures on the lander like struts. We do all of our own in-house avionics. We are an engine manufacturing company as well, and one of the challenges that we hit on this first mission was we lost the vendor who was building our RCS engines for us, and so we brought that project in-house and were able to fly those engines on our first mission, and we actually have one here at our tech demo table this afternoon. All right, so Blue Ghost Mission 1 landed on the moon in Mare Crisium on March 2nd of this year. This was a fully successful mission which operated all 10 NASA payloads and a handful of commercial payloads, almost 120 gigabytes of data downlinked from the surface, and that was utilizing what we are pretty sure was the fastest link ever established from the surface of the moon at 10 megabit. There were, as I mentioned, 10 CLIPS payloads on board, and we've already heard from some of them here at this conference, like RAC and Lister and LPV, but some of the other ones include NGLR, which was a retroreflector, RADPC, which was a radiation-tolerant computing platform, LEXI X-ray telescope, LMS, which deployed 4 probes out in the cardinal directions and then had a mast to map the lunar magnetic field. We heard from EDS Scalps. It was on this mission, as it's been on a few, and will continue to be flying to continue to study the plume interactions. And then Lugray, which was able to establish the farthest GPS GPS solution so far to date. All right, we got to the moon using a 3.5 orbit trajectory. This made use of several phasing orbits in order to target our injection into lunar orbit at just the right time. This gave us up to 7 days of acceptable launch dates per month. It also gave us about 4 weeks of on-orbit checkouts and science operations. And so this was how, for example, Lugray was able to do their operations en route to the moon and kind of step up in difficulty, first getting a GPS fix from low Earth orbit, and then from a very far distance from Earth, then in lunar orbit, and then finally from the surface of the moon. While in Earth orbit, we also checked out a number of our onboard systems. We performed calibration burns, and we did health checks for all of the various payloads. After that, we performed our lunar orbit insertion, and this allowed us to spend about 2 weeks in lunar orbit where we continued checkouts. One of the things that we checked out in lunar orbit was our vision navigation system. This system is responsible for providing pose estimation, localization, and hazard avoidance and hazard detection on our way down to the surface. And so here you can see a comparison of some of the footage that we recorded compared to the onboard rendering of that, what we expect that location to look like. And this shows the strength of the shadow rendering engine and the overall digital terrain map that we had in. Unless you're kind of up there on the screen looking at the edge pixels, it's actually impossible to tell the difference. All right, as for the landing, landing was about an hour of completely hands-off nail biting for us operators. We did not have any human interaction with the landing process based on lessons learned from past missions. And so basically we begin our DOI burn with the main engine and all 8 Spectre thrusters. This sheds a lot of the orbital velocity. This is followed by a 45-minute coast period, followed by a braking burn, and then pitch over. And from that point on, the main engine is off, and we descend with only the 8 smaller Spectre thrusters. We perform 2 hazard navigation maneuvers, two hazard navigation detection checks, and then we can locate various rocks and craters that might not show up in the LRO footage. From there, we continue to descend until a soft touchdown. That's detected both from IMUs and from our landing gear sensors. All right. I know I have very limited time, but I can't not show this video. This is the footage of the actual landing. 4 different views. Top left is looking out onto the lunar surface, and this is looking down one of the sides of the spacecraft. Top right is the top deck image, and so there you can see on the left of the top right image is the flat panel. That's our high gain array and the Lugray antenna. And the rectangular prism on the right is the LSIC telescope. And then far right, there's a mechanism there. That's the LMS mast. On the bottom left is also looking down the side of the spacecraft. It's opposite the view on the top left. And you can see one of our thermal radiators has deployed. That's what the gold MLI flapping around is. That has revealed the radiator underneath. This is a totally passive system that we actually demoed at LSIC last year. This uses shape memory alloys to automatically open and close as needed. And so that system was exercised on orbit and on the surface. And then lastly, bottom right is another camera. This one is actually looking directly into the sun. And so the small circle you see on the top right is Earth, and the very large circle you see on the bottom right is the sun. All right, we've now completed pitch over, and we are continuing to descend to the surface. We have, during this process, while I've been talking, we've performed our hazard navigation, our hazard detection checks, and we're continuing to lower. At this point, the main engine is off, and we're using pulse width, carefully controlled pulses on the Spectres to maintain attitude and to maintain our descent rate. At this point, plumes become visible as those RCS, and you can see that pulsed impact from the thrusters are causing the kind of undulating effects of the plumes. At this point now, we have cut off the engine. You can see a successful touchdown on the moon. All right, no rest for the weary, though. Within minutes of landing, it was back to business. While our mission might have felt like it was over, it was just beginning for all the payloads that this was what they were here for. And so we immediately deployed our X-band gimbal, and there it is going to face the Earth. This, like I said, had also mounted on it NGLR, which was used for ranging experiments from Earth stations, and then also Lugre, which was going to go ahead and get some GPS solutions from the moon using signals from satellites around Earth. We mentioned that SCALPS was on this mission, and so, this is not a video. This is just a view of the various SCALPS images as we came down. We saw the Lunar Planet Vac deploy and operate yesterday, but it's a short video, so we'll watch it again. This was deployed using a fifth leg, or surface access arm, as we call it. And this was deployed to the surface with a gas spring and a HDRM. We also watched EDS yesterday, and one thing I don't think we saw yesterday was LMS. This shows some of those probes deploying. It happened really quick, but now you can see the tether spooling out. And here, reminiscent of the golf ball. 1/6 gravity is a very uncanny valley. And there's the mass deploying as well. And fully deployed with the Earth crescent. We saw Lister drilling as well yesterday. And we were really interested to see what those appear to be kind of sparks, we think, from the gas that was used during that drilling. All right, so that was some of the highlights of the various payload operations on the mission. And so kind of an overview, all of these payloads met their objectives. And one thing we were able to image was the eclipse. There was a total solar eclipse as viewed from Moon, and this was not planned as the baseline mission, but due to our landing date, we were able to view that. One thing that we were contracted with NASA to do is view sunset, and so we were asked to operate 5 hours into lunar night and operate a number of the payloads. This allowed for both some unique opportunities for payloads to kind of get a control reading of what their data would look like without the sun. And it also allowed us to visualize this levitation phenomenon that some of the Apollo astronauts were able to report. And so we saw that as that glow on the horizon, which is not easily explained with the lack of atmosphere in any other way. All right, a bunch of anomalies. We calibrated, we counted about 60 different anomalies and dispositioned them. Most of them were not mission threatening. I'm probably out of time to talk about all of them, but we do have a table and we can talk about them. Some of the most interesting ones, we did have a lot more ground effect during landing than we expected, and so instead of throttling down to hit the ground, we actually ended up hovering a little bit until we continued to throttle down. And then we also landed next to a giant crater, which acted as a parabolic cooker on the lander and absolutely devastated our initial predictions of a thermal environment, and required some very innovative scrambling on our parts to keep the lander safe. This included using the X-band gimbal as a sunshade and some quick requalification of various components at higher temperatures. All right, I'd like to say that this was just an easy lift, but in fact, this was an extremely difficult thing. One of the benefits, one of the reasons we think was just because of the amount that we empowered each subsystem to take control over their own destiny and own their systems. Also, we'd like to talk about, we like to say that a lot of the success was due to the amount of testing. We had over 500 hours of sims, 8,000 operator hours of sims, so an incredible amount of preparation went into this. Anyway, looking forward, what's next? We got mission 2. Mission 2 is going to the far side, and so with each mission, we're trying to bite off another capacity. This mission will include a relay, which will provide the ability to store and forward and do bent pipe communications to this to our lander on the far side of the moon, which will be doing a bunch of radio astronomy studies using the Earth, using the moon to kind of shield a lot of the radio noise from the Earth. That's fully manifested, but what's not is Mission 3. This was just awarded, and this will also include a transfer stage as well as a lander. And this Ultra Dark will also remain in orbit as a comms relay. This is going to Groot Highs and Domes and will include a rover. So as mentioned, each mission adding new capacities. This will have a mission, rover mission operations, as well as continuing to build up that comms relay network at the moon. Okay, that's it, and I will pass it over to Intuitive now.
All right, thank you. So, hello. All right, so hello again. Yesterday you heard me talk about Hopper, and today I'm going to talk about our landers. We're going to focus on IM-2 and IM-3, but I'm going to touch on our first mission last year as well, which was our IM-1 Odysseus mission. You may recognize it. We landed in the South Pole last March, and it was the lander that landed furthest south on the lunar surface, a record broken only by our second lander this year. So that's our IM-2 Athena mission, which is where Hopper, the Trident drill, as well as the Nokia experiment flew on. A couple pictures here from encapsulation. We have both IM-1 and IM-2. We have 2 more missions coming up. We have IM-3 and IM-4 coming up in the next 2 years. So hopefully more pictures to follow. The picture on your right is a picture that you've probably seen many times in the last couple days. So that is the 2 pictures here are the beginning and end of mission of our IM-2 mission. On the left, you have soon after LVCEP, and on the right, you have our surface operations. We launched on February 26th this year, landed on March 6th. Our transit's only about 10 days, 9 to 10 days, where we spend about 3 to 4 days in open coast to the moon, and then 3 to 4 days around the moon in orbit. So it's a much quicker transit. We're doing burns every day, which also account for a much more stressful mission operations. And we're going to talk about kind of the lessons learned from all of that in a bit. But I did want to mention I had the honor to do mission ops for both our missions, IM-1 and IM-2. And as I mentioned to someone yesterday, the color purple has never looked more terrifying until it's the color that you're staring at while you're waiting for telemetry from your lander. So this is a video of our lunar orbit. Little shout out to Hopper over there. That is roughly, I believe, 80 kilometers off the surface. Like I mentioned, we were in lunar orbit for about 3 to 4 days, and a large part of that is confirming that we're ready for landing. So we're doing health checks on our sensors ongoing throughout transit. During orbit, we also do payload checkouts with a lot of our customers, making sure that their payloads are ready for as soon as we get to surface operations. And then these 2 are actually videos of our landing sequence. So this happened on March 6th, and you'll see it from 2 different perspectives. So IM-2 Odysseus gave us some of the closest imagery we have of the South Pole, and you can see how much of the surface is actually in shadow and how dangerous and hazardous that terrain is with the number of craters and boulders in the way. As Joseph mentioned earlier, like HDA, hazard detection and avoidance, is a major part of all landers. We also run those same type of algorithms that are using our optical nav system to determine not only our pace or our velocity and direction of travel, but also where is that safe spot. You predefine a safe spot in your mission ops going to start with, but the terrain, you don't get as close, we don't have imagery that's to the resolution we need to fully determine that that is going to be a perfect site for us. So HDA is a big component of what we call LDO, so our lunar descent orbit. That's when we're closer to the moon, about 20 kilometers up, and that gives us a lot more detail and imagery. We stay in that closer orbit for a few hours, and that's where we did our laser checkouts. And I'm sure there's some questions about that, and I will get to that. But I did want to touch on all the partners that make it possible. So these are our partners at Intuitive Machine across all our projects, not just our landers, but we have a bunch of NASA project partners through CLIPS, through STMD. We had a large number of payloads through them. We have a lot of international partners and corporations that work with us too. Mentioned the German Space Agency before. We worked with Nokia, we worked with Lunar Outpost, Lone Star. So we're always looking for new corporate and international partners. And then we also do a large amount of work with universities. A lot of our navigation and testing partners are universities, so they're kind of listed there. So Embry-Riddle was actually a payload on our IM-1 lander, Eagle Cam, that was going to deploy and take an image of us while we land, third-person selfie, if you will. So we're also always open to student payloads and flying them as well. So the thing I really want to focus on were the lessons learned. We've flown 2 landers now, and in our first mission, IM-1, we discovered about 85 issues that we had determined we needed to solve going forward. We had solved all 85 for mission 2. We did not see a repeat of any issue to the same flavor that we saw them on IM-1. So that was a big aspect of our retrospective, what we call our hot wash after mission. So every sub-team has an opportunity to talk about both the project build and design phases, but also the mission itself. And it was a week-long hot wash for IM-1, and we gave every opportunity to talk in a very candid manner of what went right, what went wrong, and what can we fix. So that lent itself to continuous improvement and making sure that we weren't going to have the same issues. Part of that was looking at how we test. As mentioned before, testing is a big component of making sure you're successful. And we have a large number of different interfaces and venues we do testing at. We mentioned some of the Hopper ones yesterday. We have our own flame range that we do our engine firing. So if you ever want to see what a Nova Sea engine looks like, look up a video online and you should see some beautiful firings there. But our flight engine is tested on the ground before it goes into flight. We have a lot of EDU testing that we do constantly to make sure we're improving our hardware. And we have a flat sat bench where we test every unit, every EDU unit and flight unit on the bench before it gets onto the flight hardware, the flight vehicle. And that allows us to test as we fly. So we're testing in environments that look like our flight environment to the closest degree possible. So that includes testing through TVAC, through Vibe. And that ensures that you're able to mimic an environment well. There are gaps, and that was, as we kind of discussed, laser is the big gap that we had. We found an issue on IM-1, and we solved that issue for IM-2. We tested the lasers on the ground through a series of navigation testing. However, we didn't catch a different issue, which came, and we're still investigating, coming up with the final report there, but it looks like it has some to do with interaction with the lunar surface in a way we weren't expecting. And that's where you kind of have to deal with contingencies. You can't actually test perfectly as you fly. You're not flying 20, 80 kilometers above the lunar surface on Earth. That's just not possible. And so you need to have some sort of contingency management that allows you to be able to handle such issues as they come up during mission. The big thing we learned, especially for IM-2, is that there's multiple types of contingency management. There's management that comes from issues where you have a longer period of time to solve. So it's something you could have found maybe in COAST, a thermal issue that you're seeing could trend negative, but isn't yet, and you have a significant amount of time to solve them. The way you respond to that sort of issue is different than what would have happened with our laser, for instance, where we are hours away from landing, and we need a quicker response. And you need to build those contingencies up in your training early on. So mission ops in general for these sort of missions is a complex, it's a complex engineering task. It's not just a mission design task. It's keeping your engineers in the loop and making sure that you're aware of not only the mission priorities, but of your fault tolerance, your manage your risk analysis as well. So that's something that you're continually improving on and adding contingencies. That's going to be a major part of our upcoming IM3 and IM4 missions. We're always looking for new partners, so come find me if you ever want to talk about the previous missions or the next ones.
Thank you, Neil.
Well, yep, good afternoon now. Thank you for having us here today to talk about getting gear on the surface. And I want to congratulate my competimates here, both Firefly and IM. Firefly for a fully successful mission, and I am reaching the surface twice now. I think we all know that it's very difficult. A lot of lessons learned, as we've talked about. And actually, I was surprised to see 60 anomalies you guys were tracking because you made it look easy. So congratulations. And we're looking forward to being able to deliver ours by the end of this year. So with that, I'll just, in the interest of time, move along. Lunar delivery, that's one of our key capabilities at Astrobotic, obviously. I wanted to just show our Peregrine lander sitting on top of the payload adapter, getting ready to be encapsulated in the first Vulcan launch. And this was roughly 18 months ago. I think everybody knows that we did not reach the lunar surface. We had a problem with one of our propellant valves early in the mission that overpressurized one of our oxidizer tank. And it was an interesting time. I was not there yet at Astrobotic, but I certainly have worked with the team that was there. They were able to recover basically a crippled spacecraft and fly it for 10 days in cislunar space. We were able to activate all of the payloads. Two principal investigators, as far as I know, have published peer-reviewed papers on the data they did receive. Although we didn't reach the lunar surface, we were actually able to elevate most of our subsystems to TRL 8 or 9, and that feeds into our next mission, which is Griffin Mission 1. This will be the largest lander, commercial lander, to go to the moon through the CLIPS program. Kind of call it a medium-class lander, capable of delivering 650 kilograms to the lunar surface. That is a picture there in our clean room. We were doing a fit check of our solar panels. That was about a month and a half ago, and work continues. I'll talk about some of the progress here. Mainly our main payload is Astrolab's Flip rover. Great team to work with between Astrolab and Astrobotic. And so we're really looking forward to delivering that rover to the lunar surface. And we also have a couple of international payloads as well that I'll just briefly touch on here. So here's a video. Not sure if you need to activate it or...
Just hit next again.
Yeah, there we go. So I decided not to play the music. I won't walk it through, but this is a rendering of Griffin delivering the Flip rover to the lunar surface after a ride on a SpaceX Falcon Heavy. As I mentioned, our launch window opens up in December. And we hope to show a year from now at the LSIC Spring 2026 meeting actual video like Firefly did with their mission. As you can see, we've landed in the South Pole region, and the Flip rover will be deployed onto the surface via ramps and a tether. Once they've activated their rover and they're ready to go, then the tether will be detached and Flip will go off and achieve their mission objectives. And as I said, we've got some additional payloads that'll be flying on board, so the lander will continue to operate for 14 days and acquire data for the principal investigators of those payloads as well. So one of those is being developed by ESA. It's called LandCam X. It's essentially a camera that is testing out some navigation algorithms with the intent to improve the accuracy of landing for future landers. So we're excited about taking on this international payload. And also, I'll talk a little bit more about Cube Rover Run here in a couple slides. That rover has been developed by Astrobotic. It's an in-house development, but we are partnered with as a joint mission with Mission Control Space. It's a Canadian company that's being funded by the Canadian Space Agency. They've developed a software platform called Spacefarer. Once we've deployed Cube Rover onto the surface, we will, as a company, will basically drive our rover on the lunar surface, check out some systems, and then we'll turn it over to Mission Control for them to do some mission objectives with their software package. So we're pretty excited about this joint mission, and again, it's another international partnership. So there's another picture, more close-up of the Griffin lander. You can see it on the stand in our clean room. Again, those solar panels are now off and being finalized while we're doing some additional AI&T work on the spacecraft structure itself. So some key components here, propellant tanks. On the far left is the qualification tank for the tanks that are being made by Vivace. And then the picture right to the lower right of it is flight tank number 2 being welded together with the barrel section and the dome sections. They've made much more progress since then. These pictures are probably a month old. And then on the right, the qualification axial engine being built by Frontier. It just finished up Shock Vibe last Friday. And we are looking at the data along with Frontier on that. We're looking forward to actually doing the qual engine hot fire here, hopefully in June. Frontier will be running that at their test stand. That's actually at Exquadrum in Victorville, California. So we're getting very close to getting flight engines as well. And then on the far right is, it's kind of a faraway picture, but that's our Universal Test Campaign test article. This is a mobile test article that we originally built when the Viper rover was going to fly. NASA wanted us to do some additional testing to increase the confidence on the propellant and propulsion systems. We decided to keep that with in partnership with NASA to go ahead and do that, even though Viper is no longer flying on Griffin Mission 1. That test article is near completion. It'll be done in about 2 weeks. And then we'll be sending that out to Exquadrum as well. We'll be doing cold flow testing and hot fire testing with some ground thrusters to characterize the propellant system, which mimics the Griffin lander propulsion system. So it'll be always good to see some smoke and fire coming out. TRN and hazard detection. We have developed our own TRN HD system. And in fact, just within the last couple of weeks, we successfully completed sims with injecting issues to adapt to those issues and do successful landings on the lunar surface from a flight sim standpoint. So very proud of the team of working through those sims. We'll continue to do those, but we're pretty excited that we made it through the simulations to date. Now I'm going to show you a video in the next slide, but you'll see on the right is our Zodiac vertical test, vertical landing suborbital rocket that we fly out of Mojave, California. The reason I'm showing this is we flew our TRN HD system on board that over a simulated lunarscape that we have out there called the Lunar Surface Proving Ground. You can see in the top right and then on the bottom right at a nighttime shot of that. It simulates a lunar surface. Not only have we developed tested out our TRN HD system, but other commercial companies and have tested out some of their landing algorithms as well using our Zodiac vehicle. So this is just a quick video to show an actual flight. It goes up to 500 meters, and you can see the Lunar Surface Proving Ground over there to the left on that, and then it returns to the same launch pad. And this vehicle has flown over 600 times. In fact, they flew a free flight yesterday. So full manifest on that. It's a good test bed. Cube Rover Mission 1, I mentioned earlier. Here's some pictures here of the engineering model on the top left. We sent that to Mission Control in Ottawa, and we actually were able to send commands from Pittsburgh, where our Mission Control Center is, to the rover in Canada in their lunar surface test bed. And then when the engineering model came back, we reversed that, and Mission Control sent commands from Ottawa to our headquarters in our test bed, all successful, and so we'll continue to work some of those tests. And with that, just to let you know that the flight model is near completion, and we hope to have an announcement here in a few weeks on the progress of the flight model itself. We've tested out the deployment system for the lander itself, all successful there, so we have a lot of good progress going on, and we're looking forward to sending Griffin and the flip rover and those payloads I mentioned at the end of this year. So thank you.
Hi, everyone. My name is Jeremy Fix. I'm the Chief Engineer for iSpace US. And before I tear into it, I want to thank LSIC for putting this on. This is fantastic. APL for hosting. Adam for corralling us all up here and making us behave. And our fellow panelists. But most of all, I want to thank you, the audience. If it wasn't for your passion and your interest, there'd be no point in us being here today. So thank you for attending. I know I'm going home this week re-energized, ready to get back after it at work. While I represent iSpace US, a lot of the successes and accomplishments I'm going to be talking about here today are really owned by my Japanese and European colleagues in Luxembourg. Just want to acknowledge that. It's a lot of their hard work, their accomplishments that we're building on. Part of our vision is really trying to work backwards from a lunar economy in the future. I think you can get caught in the here and now. What am I doing today? But you really need to be looking forward, where are we going to be in 15 years? Where are we going to be in 20 years? And I would encourage you, I don't have time to talk through it today, but I'd really encourage you to go Google Moon Valley 2040. Look at our long-range plan as a corporation. I do that myself. Some of the days you get frustrated, you get kind of stuck in the mud. Jump on there, look at the future, look at a lunar economy. You can't have an economy without people. I guess you could build a robot economy, but there's a lot of sci-fi says that's not a good idea. But really building forward and really thanking everyone here for the openness. We're treading new ground together. We're going places no one's gone before. Really, iSpace US, our parent company, iSpace Incorporated, founded in Tokyo, Japan in 2010. We have since grown strategically across the world in Luxembourg and Europe and here in Denver, Colorado. That's intentional. It's a global footprint, global collaboration, not only with the international agencies, JAXA, ESA, NASA, but we also have access to the global commercial companies. One key and right now we're a little over 300 employees worldwide, 100 in the US, and I'm very proud to say we have over 30 nationalities represented within the company, so we truly are a global company. One key enabler, we were able to secure a State Department approved technical assistance agreement with Japan and Luxembourg, which means we can freely share lessons learned, successes, technology, not only in software, hardware, across the board. It really kind of helps us work as an international body. Within the iSpace US, to date, we've had over $120 million of investment in our site in Centennial, Colorado. A lot of our vertical integration is occurring there, a lot of our propulsion system building, avionics. This also houses our Mission Control Center for future missions coming up, in addition to the one in Tokyo, Japan. Our team right now in the US is sitting on console with our Japanese colleagues with Mission 2. As that mission completes, that same team will come back to the US and sit on console for Mission 3. So we have a continually trained up group of mission operations globally that can support each other, and both of these sites can act as a backup to each other for future missions. Kind of walking through hardware on the left, Luxembourg is really our mobility expertise. Right now we've got the tenacious micro rover, about 1 kilogram of payloads. It's great for local area sensing, interrogation of the regolith, manipulation. The Resilience Lander, that is the first mission out of Japan, delivers about 30 kilograms to the surface. It's right-sized for a ride share on a Falcon 9, and in fact, Mission 2 was co-manifested with Firefly Blue Ghost, January 15th. They got there a little bit sooner, but it's not a race. And part of the realization is that you're making a huge investment in going to the moon, not only in the launch vehicle, the people, the capital involved. You really have got to up the amount of mass you're taking to the surface. And moving forward into the future, Apex 1.0 is the vehicle being designed here in the US, complementary with the Series 3 lander in Japan. Both of these vehicles share a lot of common components, including the engines, some of the avionics to the extent possible. The differentiator there is that Apex 1.0 is dedicated or really designed around the Falcon 9 GTO capabilities, where the Series 3 can also support the Mitsubishi H3. If you have a customer with domestic sourcing requirements or certain launch requirements, we can support either. Talk a little bit through Apex 1.0, our US lander. It's a large vehicle, not as large as some others up here, but we do have the ability, multiple payload zones, standard interfaces. We offer a lot of compute capacity on the vehicle. Your terrain relative navigation, hazard avoidance requires a lot of computing capacity. We make that available to our payloads after landing. We did stick with storable propellants, a lot of propellant margin coming in and landing, really trying to bring in exquisite landing capabilities for our customers wherever they want to go. Bigger picture, I think the lunar scape is evolving to where you have these very large landers that'll have maybe a very large anchor customer that'll take a lot of people to one site. Kind of the SpaceX transporter model. I kind of compare that to the cruise ship model on Earth. If you want to go somewhere fun, you can leverage the capacity of buying power of a bunch of people, but unfortunately you don't control where you're going. You're going to sit in the same stateroom. You're going to have the same meal plan as everyone else. Where we're targeting is customers who want to go have a specific location, a specific time, a specific mission that they want to go to, where we can provide really a full end-to-end mission as a service for outliers that really have special requirements or special capabilities required. We also are developing, as part of our commercial mission 3, for anything going far side, you don't have direct-to-earth communications capacity. We're developing multiple instantiations of the same vehicle of a relay satellite. Provides high bandwidth direct-to-earth communications relay services that will service the lander on the surface during its primary mission. These will carry on and continue to operate long after that mission terminates. There is relay capacity. We're looking to use that some of our own landers, but that's also available for other customers if you need that service. I would point to, back to my previous slide, looking at these landers, there's nothing that would prohibit these vehicles from living for years and years on the lunar surface if you can survive that brutal lunar night. And we do have a couple of strategic cooperations in place with Volta Space Technologies and Xenopower to really start trying to build these vehicles to where they can not only survive the lunar night, but operate through. Hop through that. Really kind of the most exciting is Mission 2. Again, it launched with Blue Ghost on January 15th. It is now in lunar orbit around the moon. We're coming up on a landing here very soon. The vehicle itself, some commercial payloads, as well as the micro rover out of Luxembourg. Some pictures. I think if you go on the internet, there's almost as many pictures of the moon as there are of cats. But this one is special. This is really our success number 5 of our lunar flyby and our low energy transfer. Another shot looking back to Earth. If you're sentimental like me, this is a little bit of a sad photo. You've got an explorer leaving home, never coming back, kind of looking back over your shoulder, knowing you'll never return. Mission 2 milestones. There are currently 10 of them. We're right now at success number 7. We have entered lunar orbit and are rapidly approaching the probably the most critical and most complicated sequence of events to actually get to landing and touchdown. I would invite everyone to join us in the landing party, June 5th, 1524 Eastern Time. You can scan the QR code. I promise not to rickroll you. Or you can go to the iSpace Landing site. There's a lot of information, not only on the mission, everything leading up to it, but it's going to be very exciting. We'd be honored if you would join us. Post-landing, where the mission really begins, is the mobility portion of the mission, where we will deploy the rover. Again, we're not calling these milestones or gateways. We're calling them ventures because you have a mobile asset. One is getting it, commissioned, deployed, operational, moving around. I'm happy to note this will be the first European-designed rover that is teleoperated on the moon. It does have a scoop, and another kind of a novel feature of this is we are going to actually collect lunar regolith, and under the Artemis Accords, do a transfer of ownership of that regolith from iSpace to NASA. Even though it's never going to come home, we're starting to exercise these stepping stones to getting us to an economy on the moon. Last one I'll close out with, our own mission out of the U.S., it's the Team Draper Commercial Mission 1. This is the NASA CLPS CP-12 mission. We're proudly supporting that entire payload manifest, as well as a few more commercial payloads on board. Would be very excited to be able to come back here about this, late 2027 and tell you all about this mission when it closes out. So anyway, thank you everyone. I appreciate your time today.
Thank you. Hello. Can everyone hear me okay? All right. Awesome. Thank you. Hi, I'm Jackie Cortez. I'm Senior Director of Civil Space at Blue Origin. Just wanted to start by saying that I've been at Blue Origin for 8.5 years. And the entire 8.5 years, I've been lucky enough to be working on enabling our lunar projects the entire time. So I'm very excited that we're making our first moonshot this year. It's been a long time personally for me, so I'm very excited. And I would just say longtime LSIC fan. So thank you all so much for having me today. For those of you here yesterday, some of these charts will look like John's. He stole them from me, not the other way around. But I will hopefully tell you some things that you didn't hear yesterday from him. So for starters, one cool thing is that Blue Origin is making 4 moon attempts this decade. So prior to 2030, which I think is something that a lot of people might not know. So our first one is the Mark 1 lander, the lander in the center of the screen, which we are attempting a South Pole landing this year, 2025. And if successful, it'll not only be the largest lander to ever land on the moon, but also the only LOX hydrogen lander. So that's a commitment by Blue Origin, a long-term commitment. We consider ourselves a bit of LOX hydrogen experts. We've been doing it for a very long time on our New Shepard vehicle that hopefully people have seen launch and land on a regular basis. And so that's a big one for us this year, is that first Blue Moon Mark 1 lander. Our second Blue Moon Mark 1 lander is also in assembly at the exact same time as the first lander going to the moon this year. So that's very exciting. We have a dedicated facility in Port Canaveral, Florida, where we're building all of our Mark 1 landers. We intend for it to be a production line capability. It's a 3,000 kilogram class lander. We went straight for an infrastructure class single launch capability, so I'll talk about that more in a second. Our third mission to the moon is going to be our uncrewed human landing system demonstration. So that team is hard at work also down in Florida building our systems for the human landing system program. That uncrewed demo can also fly payloads as well as both of the Mark 1 landers. So that's our third mission planned to the moon this year. And then prior to the end of this decade, we'll be landing 2 crew on the lunar surface for NASA in partnership with the Artemis program. So a lot on the plate for the team, but we're very excited about these opportunities and these various moonshots. So it's very exciting for us. But mostly here to talk about Mark 1 today. So we'll quickly hit on some key points that hopefully if something again that you didn't hear yesterday. But again, this is a 3,000 kilogram class lander, and it flies on a single New Glenn. Hopefully people tuned in January. We flew New Glenn for the first time and achieved orbit within pinpoint accuracy on our very first mission. So that was a huge moment for Blue Origin and a key enabler of everything we're doing in our lunar permanence business unit. So this lander is powered by one BE-7 LOX hydrogen engine, a 10,000-pound thrust engine, which again is part of a broader Blue Origin commitment to using LOX hydrogen as our core propellant mix to unlock the greater solar system through technologies like zero boil-off, other cryocooler technologies. This first mission this calendar year I'm so excited. I actually have so many hardware photos, but we're saving them for Twitter, unfortunately, so I did not show them. But Mark 1 is very far along in development, in assembly, as you would expect for a lander flying to the moon this year. You'll just have to take my word for it right now, as this is a render. But we're actually in final assembly right now to ship the vehicle out to NASA Johnson Space Center here very imminently for testing at Chamber A, which is we're very grateful for that partnership with NASA. After that, we will head back to Cape Canaveral with our cute little Mark 1, and we will launch it to the South Pole of the moon. The transit's about 7 days from launch to landing, and again, headed to the South Pole. One thing that I think is really cool, and I know we're all probably huge procurement nerds here, so we are a CLPS vendor, which a lot of people don't know. We are on the CLPS catalog with the Mark 1 lunar lander, and one amazing partnership, and we're so grateful, is that CLPS realized, in partnership with Blue Origin, we're not going to miss a shot at the moon here. We're not going to miss an opportunity to fly some really exciting science to the moon, despite the fact that Blue Origin fully self-funded Mark 1, and there was no government resources that went into this vehicle. So CLPS did a partnership directly with Blue Origin, and we are flying a plume surface interaction camera system in partnership with CLPS, SCALPS, which has been mentioned by several others, and I think the message and what I think is so cool about this that I'll share is we should not, as a community, be missing any of these missions to the moon. We should maximize as much as possible. Everyone here has lots of missions going, and certainly we should make sure we're getting as much data as humanly possible. So again, very grateful to Adam and his team for going a little bit outside of the typical task order process to make sure we're getting valuable data in plume surface interaction from an engine that is significant, 10,000-pound thrust engine. So that data is going to be very valuable for this community and for all of us as it comes to that important regolith interaction. So again, very grateful for that, and to be a CLPS vendor and to be a CLPS task order provider. And like I mentioned, our second Mark 1 is simultaneously in assembly. So our facility in Port Canaveral has one lander almost done and a second lander in assembly. It was really important for us to procure all hardware for 2 Mark 1 missions years ago. I think that's a key finding, is that supply chain for single-use items is very, very difficult in the space business. So we went ahead and procured all hardware for 2 Mark 1s several years ago. So that lander is in assembly, and ideally we'll have a successful first mission of Mark 1, incorporate any findings and be ready to fly again. But also in the event that, there's more to do, or, the mission doesn't achieve all of our objectives, we have another lander ready to go. That was something that was really important for us, and we do have payload space available on the second Mark 1 for those people that are looking to go to the moon here soon. So that's another exciting thing. John showed this yesterday, again, stolen from me. I actually made this chart, but just to show you all some hardware, since I wasn't allowed to show the lander. But we have Mark 1 hardware for the BE-7 engine on 4 simultaneous test stands. So hardware rich is a key part of what we're incorporating into our lunar efforts. So these are just some examples. We're starting the engine nearly daily at AFRL in Vacuum in California. We have 2 stands programs in amazing partnership with NASA Marshall in Huntsville, and we have our own private engine test facilities in West Texas. And before I conclude here and let you guys get to questions, I did want to say that we are very, very thankful for all the work that we do with NASA, and I just wanted to share some opportunities to work with Blue Origin. For example, we've been working with STMD pretty much since the beginning of Blue Origin, largely through the Flight Opportunities Program. For those of you that are unfamiliar, it funds flights on vehicles like Blue Origin's New Shepard. And that vehicle has been a test bed for us to advance all of our lunar capabilities, like John mentioned. We've flown DDL sensors on the booster, and we recently, in partnership with STMD, actually flew a dedicated lunar gravity mission. We've spun the New Shepard capsule to simulate several minutes of actual lunar gravity here on Earth. It was a fully booked mission by researchers, NASA, and Blue Origin to test our capabilities long before we ever fly to the moon. So that is an amazing mechanism, and I would highly encourage everyone to look into it. Many tipping points that we're so grateful for with STMD, our deep partnership with CLIPS, who I will just say, you know, being the lunar lander experts at NASA, they help us with so much more than just our little task order. So we're very grateful for that. And then, of course, the Human Landing System program. We would love to talk to you guys about payloads, so find me whenever. And yeah, please keep your fingers, toes, anything crossed for a successful first Mark 1 mission this year. Been a long time coming for a lot of people at Blue Origin, so we're very excited. So thank you.
Yes, I want to thank all the panelists again for talking about some of which is behind us today, but more excitingly about what's in front of us. So definitely an exciting time for CLIPS and the broader community. We do have a little bit more than 10 minutes for questions, and there's several in the queue. But just a reminder that please enter them if you have one. And we'll jump right in with the kind of the highest voted one, and I'll start it with Joseph. CLIPS is definitely a community, but it's also a competitive environment. How do you balance preserving your competitive advantage and collaboration and data sharing between other lander providers?
The other chief engineer on the Blue Ghost program, Dr. Coogan, was talking to an old colleague of his just the other day who worked on the Apollo missions at Draper. They met in university. And his colleague was saying how it was a shame that a lot of the data they have from his work, he was in GNC for Apollo, and a lot of his work is gone. And so that kind of inspired us to continue to do what we've already been doing, which is applying to a lot of conferences and submitting a lot of abstracts and papers. I already know for a fact that we'll have papers coming out from the flight dynamics team, our propulsion team, our thermal team, and a lot of the other teams will be continuing to publish those papers so that all of the learnings that we have can be applied to other companies and for the United States and humanity in general to continue to take steps forward in the exploration of space together.
I'm going to echo a lot of that. Many of you are probably really familiar with some of our execs, Tim Crane, Steve Altimus, Ben Bussey. They come to conferences regularly and like to talk about our missions. Also, a large part of why I had a specific lessons learned slide today is I wanted you guys to get the information you're not seeing online. You can learn about the lander capacities online, but the detailed workings of how we did mission control and the lessons learned from an operator and those of us in the room are important. So conferences like this, to LSIC and APL's credit, is super important to bring this community together and having these open discussions and being candid with one another about what works and what doesn't work. It's super important.
Yeah, and I think I mentioned during my talk, I said competimates, and that's really the culture I think that NASA CLIPS has built with the CLIPS task orders. We are competitors, but we all want each other to succeed because we really need everybody to succeed if we're going to develop this lunar economy that we all want to get thriving, right? We're right at the nascent steps of it now with getting to the lunar surface, and we just need to continue to have successes to build that lunar economy, not just for the U.S., but really for a global community. I mentioned too that Peregrine had an issue, and we released a review board report last year, about a year ago now, so that we could share those findings with the broader community so people could learn from what we experienced, and so they did not have to go through that as well. And I think that had a ripple effect too, all the way down to the supply chain. Jackie mentioned supply chain. It is so critical, I think, to have a strong supply chain for all of the CLIPS providers going forward. And that means multiple missions that need to be awarded. I know Adam and his group are looking at a CLIPS 2.0 eventually, and we hope to see maybe a more robust supply chain structure there where multiple missions are awarded so that we can really secure a good, strong supply chain base, again, for this lunar economy that we all want to establish.
I view this as we're not trying to corner the market, we're trying to build the market. Everyone here is helping each other to do that. We don't know where it's going to head. We don't know how big it can be. But knowing that we're collaborating, we're working together to build the market, to build room not only for everyone here, but for others that want to enter it, to build it on. And I really look at it as we're the incubators, not the competitors. It's a huge market, a huge potential, and it would be very short-sighted to try to grab onto a piece of that and not grow it together.
Yeah, I totally agree with what everyone has said, and we're very grateful for how open all of the preceding missions have been. We've incorporated a lot of findings from the preceding lunar missions into our conversations. We've challenged ourselves, and we're so grateful for that openness that everyone has shared. So I'd say that first off. And second of all, we're always looking for opportunities to collaborate, and like Jeremy was just saying, the CLIPS community is the perfect place. So for example, with some of our visions for in situ resource utilization on the lunar surface, a key enabler of that is mobility. And so we've always had mobility visions at Blue Origin. And a couple years ago, we acquired Honeybee Robotics, who are experts in off-world mechanisms and mobility type work. And we, because of this, wound up partnering with Firefly for their mission to the Groot Hyson Domes, and we're the mobility provider for them for that mission, which is very exciting. So it's just another example of how, I agree with you, totally CLIPS is an incubator for broader collaborations. It's not just one of us, but all of us, and we're always looking for opportunities like that. So we're grateful to be partnering with Firefly on that.
Thank you. All right, next one I'll direct to Niharika, and then I'll see if Jackie or others have any comments. And several folks talked about the challenges with the South Pole landing sites. What are you considering for de-risking some of those challenges for future missions?
So we've talked a lot in the last couple days about testing, and I'm gonna go on a little bit more about that. It's characterizing your testing to fit your environment. So some of the challenges we've talked about at South Pole are long shadows or really deep craters and a lack of imagery that we have currently. So you start building newer navigation algorithms that help you use different sensors. So we wouldn't necessarily use the same sensors we used in a previous mission for maybe a further South Pole mission. We look back at our lessons learned and how we interacted with our sensors, what the performance for our IMUs were like. How clearly did we see our imagery from our cameras? And we got a lot of imagery during this last mission. So we're really looking at all of that in intense detail to determine, do we need new sensors, or do we just need to advance our algorithms? Do we need to test in a sandbox that allows us to mimic regolith reflection, for instance, or study our cameras in an area where we could create these long shadows created by craters and check what our performance is looking like there.
Anything you want to add?
Yeah, I'll go ahead and add. I think, South Pole presents a lot of unique challenges. Our landing site was in Mare Crisium, which is kind of mid-latitudes, a little north, but mostly, mid-latitudes. But we did land very, very early in the lunar morning. So, I mean, we've looked at our vision navigation system. It's, we think, resilient to sun angle of down to 2 degrees. So we think it would be pretty robust, and it certainly was very robust on our first mission. But that said, I think we're going to continue to watch progress of other landing attempts and continue to keep our eye on other sensors, perhaps leaving the visual domain if we need to.
Next one I'll originally direct to Steve, and then I'll poke Jeremy and see if anybody else has a thing. It's beyond a successful landing, what are the most critical operational data points or feedback mechanisms your teams need from the lunar surface to inform future mission design and improve reliability for subsequent deliveries?
Well, that's a good question. I think to touch on what we were just saying right here is landing in the South Pole environment is hard. Right? We can land at the mid-latitudes and so forth, full sunlight, but I think the fact that we're going to be landing on the South Pole as well, and that's where we think, again, that we're going to have a human return presence there. The more we can land there, the more data we can get from all of these landings, and then share this data will only improve the accuracy and the precision for our landers and the future landers, even the human landers as well. Which is critical. So if we're going to build a base basically in the South Pole area, we need to be able to land with really good precision in different areas around the South Pole so that we can expertly build out the infrastructure that's needed there for more permanent presence. So again, coming back to these early shots going to the South Pole, the more data we can get from these landings and we can share across so that we all can really refine and dial in our precision landing, hazard detection, and so forth, I think is critical. And then we can start laying in the infrastructure that we need to put in place, such as power, so forth like that.
Anything you want to add?
Yeah, from our perspective, all data is good data. Some of it is useful. We've been extremely lucky to have access to it, to other pathfinders already. You know, a lot of lunar maps in Viz have been done. But again, South Pole gets tricky because the scene doesn't look the same as it does in the picture, right? You've got shadows, you've got the sun playing tricks on you, you've got the sun trying to blind you perhaps. And a lot of that is moving to sensor diversity, moving to sensors that don't rely on sunlight. And again, moving forward into the future, we're going to want to be landing on unlit surfaces. There might be items that drive that, better terrain sensing. Mm-hmm. And really, the best way to drive that is modeling what you can, test, and there's really no replacement for that. Test what you can. In relevant environments. It's easy to fool yourself that you have a solution that works. It's a little bit harder to really bang at that until you know you have a bulletproof solution.
Have time for just one more question, and I'll start down with Jackie and work our way back. You know, one of the big tenets of CLIPS is lessons learned and lessons applied, and we saw that kind of mentioned in multiple of the presentations. So I just want to ask everybody kind of to identify your one or two kind of key lessons learned to date, whether it be in the lead up to a mission or in the execution of a mission, and how those are being applied to future missions.
Yeah, that's a great question. Like I mentioned, we are very grateful for the lessons learned shared by others, and we have incorporated that, as I've mentioned. I would just say for us, the biggest lesson learned so far has just been hardware richness and some of the supply chain issues that I think we've all encountered. It can really make or break your mission. So like I mentioned with our BE7 example, you know, I think we might have been a little slow going at the beginning because of, you know, issues with hardware richness. And so the number one thing we realized that we could do is, you know, partner more, acquire as many stands as possible. And frankly, like, even if it doesn't work, test as much hardware as you possibly can. And so, like I was mentioning about never missing an opportunity to take something to the moon and learn something, we've tried to never miss an opportunity at a test stand, never miss an opportunity on New Shepard to fly and advance something, because hardware richness and making sure that, you know, you've done as much as you possibly can before taking that moonshot is something that we're trying to apply. So the BE7 example is probably the best one from us.
From my perspective, I'm a technical animal. I want everything perfect. I want it to go right. But really learning to step back and balance schedule, risk, and cost into that equation. We do not have infinite funds. We also cannot afford failures. And honestly, the biggest heartbreak would be getting almost to the finish line and then not being able to go and pull the trigger and see what happened. And we've got to balance that all the time. If you take too long, if you test too much, if you spend too much, if you have setbacks and you don't run the risk, then maybe you aren't going to get the chance to go there. So it's really learning. It can't be perfect. It's got to be good enough, and you've got to put your risk and manage it where you can.
Yeah, and I'll kind of pull on that one. Good is good enough. We've learned too to balance that with test, right? You got to find that sweet spot where good is good enough, but you want to make sure that you have tested and bounded what you think would be all the failure modes for those different systems. Again, we did that for Peregrine, and we thought we had a good handle on it, and we thought the valve that failed was actually, it had been tested beforehand and worked perfectly fine, and then it failed on orbit, right? So definitely want to do test. Along with the supply chain, I got to keep touching on that though, is we've learned that you need to really do your due diligence when you look at suppliers. And I think it helps once you've selected your supply chain in certain respects for maybe the major subsystems, is to be somewhat embedded with your supplier through development, through testing, ensure that you've got very clear requirements for them to develop, qualify, and test to your specifications. We've also learned that sometimes there's room for interpretation. I'm a big advocate, and this is probably my NASA background, is have explicit requirements and sign up to those ahead of time.
I'm going to take tests a little bit further and say, how do you integrate your testing results with your contingency planning? So circling back to what I kind of talked about earlier, what testing have you completed? What testing are you unable to complete? And how much risk have you brought down versus how much risk still exists in your system? And when you look at that holistic picture, what contingency planning for mission do you need to complete ahead of time? Do you need to have certain software patches ready? Do you have a computer reset procedure already in place? Do your operators know how to recognize the risks when they actually occur? Or do they need to be trained up in that further? So once you start looking at your holistic picture, it's you're taking a step back, your vehicle's built. Maybe it's shipping to the Cape, maybe it's a little bit earlier than that. What's left? What were you unable to do? And how will that end up showing itself in mission? That's going to be the things that show up in mission, is the things that either you didn't think about or the things you couldn't deal with. So it's all both the known unknowns and the unknown unknowns.
Yeah, after, I think I mentioned after we landed, it was like no rest for the weary, the real mission starts now, and thankfully this lesson was not learned the hard way, but we had spent a lot of time before the mission preparing for the first couple of hours, the first couple of days on the surface, and that was time well spent. I think everyone was a little surprised by just how much had to happen all at once, right away, as fast as possible. We had 10 NASA payloads on this mission. I think that's the most that's been manifested, and I think CLIPS is like, oh, that was a lot. We should maybe rethink that. It certainly was a lot to handle for us as well. And so there was just a lot to do really quick. And also I mentioned we had the overheating problem from the crater. That put a lot of pressure on getting payload operations done and as those temperatures continued to climb faster than the models predicted. So don't just practice getting there, practice the surface operations as well. And that'll it just goes to, really ensure mission success all the way through. Thanks.
All right, so that's going to conclude this panel. I want to thank again the panelists and LSIC for hosting the topic. As several folks kind of alluded to, hopefully future LSICs were able to see a lot of the success stories or the future missions in front of us. So thank you all.
Thank you. Okay, it is time for lunch, but before you go, I just want to mention that we do still have the Slido poll open from this morning. You can just flip to the next tab and answer your Slido polls, especially if you have to wait to pick up your lunch. And we do have a bunch of rooms open for continued discussions with the capability areas, as well as one for the open lunar networking. They're trying to build a platform, and they want to talk to you about it. So go see them too. Thanks. See you guys at 2:30.